Hey everyone, this is Dr. Aeronautics. Welcome back to episode 2 of the planning of the Orbiter Saturn expedition of summer 2021. You may have remembered in the last episode, we basically determined where we would go and what vessel we're going to use. Today is what is called full mission planning. Mission planning is exactly what it sounds like. We developed the mission. Now we have to plan the mission. What happened last time was the easy and the fun stuff. Now we have to start number crunching, and unfortunately, there's no real way around this. If you want to fly a realistic space mission using less than Star Wars like technology, it's going to involve quite a bit of working through things in order to do it. So I have 14 phases. The first one's going to be pretty easy, adding vehicle to the mission info. You remember we did a trade study last time, and we selected that the XR2 Raven Star was going to be the vehicle that we're going to use. And because this will be an exploratory mission instead of a commute, you may have remembered from my orbiter commute to the Blue Ball system, I used the Raven Red skin, but in a slightly less developed space, I like to use the Angel Red. That's sort of my skin for going out and pioneering, basically the first mission to X, Y, or Z, which is basically what we're trying to simulate here. Now the last section is to perform a final inspection, so is likely longer than 14 stages that we need to do. But the very first stage of adding the vehicle to the mission info, that's done. That's real easy. And it's going to get exponentially hard. And I really do mean that. At least up until the sixth step. Alright, so the second step is to add the list of destinations in order on the flight table. So we basically have them here, right? I said we're going to Saturn and we're going to see the ring F and Enceladus. And in fact, I've made just a few changes to the plan. I think I had mentioned that I was planning to dip into Saturn's atmosphere, but in between making the last episode and this episode, I decided that the smarter decision would be to take the atmospheric probe and then approaching Saturn, release the probe, and then maneuver the path, and it will only take a few meters per second, hardly any engine power to safely avoid the atmosphere for us. And then what we'll do is we'll adjust our planar alignment so that we're flying in at a low inclination to begin with, and then we'll pass inside the inner ring boundary, inside I think it's the B ring is the lowest ring. Whip around Saturn, and then we'll get out of the lower ring area, and then once we get back outside the E ring, then we'll circularize our orbit so that we never go through the rings again. That is basically a decision that I made to be able to do the same maneuvers for less amount of fuel. So for example, we're still going into the atmosphere, and in fact, instead of just sampling the high atmosphere, we're diving deep with the probe. The probe is going to go down into the atmosphere to really several bars of atmosphere until it fails. So we'll get more for less, really, which is actually really cool. So anyway, so we're going to put the home planet, so we're originating from Earth, and then we're going to fly to Saturn, and then it's kind of blurred together because I'm more interested in orbits here. So we're going to visit Saturn, the ring, and drop the probe all on the same approach orbit. So I'm going to consider just leaving it Saturn there. And then we're going to, what was that? I thought Earth. Enceladus again. And then Iapetus. And we're actually going to need to add a line here. Whoops. I jumped the gun. This is Titan. And then Iapetus. And then we're going to return home to Earth. And that time we want the autocomplete. Okay, so I'm going to take a look and make sure that we have this put in correctly based on my previous flights. Okay, so the flight order's correct as is. We're going to leave it alone. We can't touch the launch dry mass for the time being. And the phases table we're going to be filling out later. Okay, now moving down to our phases table, this is going to be critical to thinking about how we're going to maneuver, right? So I made a couple of changes ad hoc, just in thought, and I haven't applied them to the table. So we're going to do Earth to a low Saturnian orbit. But the orbit is going to swing from basically all the way down to the haze tops of Saturn up to the level of Enceladus, approximately. So that's correct as is. And we will visit the F-ring in that orbit. So we're actually not going to transition from the F-ring. So we'll get rid of that segment. And instead of F-ring, we're going to say low Saturnian orbit to Enceladus. So basically what we're going to do is we're going to come in and I will talk a little bit more about how we're getting there in the first place. But we're going to come in, we're going to go all the way down to the haze layers of Saturn, and then we're going to fire the engine, and we're going to lower the upper approach from an escape trajectory of Saturn down to the level of Enceladus. And what that's going to do is take us up on an Enceladus transfer. Now, more than likely, Enceladus won't be present when we arrive at Enceladus's orbit. So then what we do is we figure out, okay, where's Enceladus now? And then figure out, okay, how long will it take for Enceladus to get where my orbit crosses Enceladus? And then at the top or apogee of the orbit, we're going to burn the engines to increase the perigee off of Saturn's haze tops, higher up above, but not under any risk that we would run into the rings. So we'd have a slightly oval-shaped orbit, go around one or more times as necessary until at the apogee of our orbit we link up with Enceladus, and at that point we have our rendezvous. So that makes it a little bit easier from the fuel perspective. And then it remains unchanged. Enceladus to Titan, Titan to Iapetus, Iapetus to Earth. And that's the mission. Okay, so this is one of the most grueling processes now. We're going to list the maneuvers in the maneuver table. So everything in the mission, every time we have to fire the main engines or the hover engines or the retro engines, we have to make an entry here. So we get the phases from this upper section here, so that's why I put these phases in. The other thing that we're going to have to do is start thinking about what kind of orbit we're going to be on. And that helps us visualize the maneuver that takes place, right? So let's start out at the very beginning. the first phase is going to be Earth to low Saturnian orbit. I originally said middle Uranian orbit because that was this was slightly copied from last time in an effort for me to recall certain nuances about the table. So everything in the table except columns F through J is going to be filled out today. Yeah, this excluding the shaded region all the way down to here and probably more. So let's get started, right? So where did I say we're going to start at? Wallops Island. So picture Wallops Island. I'm on the Atlantic seaboard. I'm a couple miles inland from the coast. There's an airport that looks a lot like a typical international airport. And there's hangars on aprons surrounding it, just like any airport. And we're sitting just outside of a hangar on the tarmac. And we're going to do our mission. So, starting the Earth to low Saturnian orbit, phase, there is no orbit, right? You're sitting on the ground at Wallops Island in front of a hangar. What's the first thing you have to do? The taxi. So we're going to go ahead and list, but not solve right now. So that's the very first thing, right? Where does the taxi take you to? The runway. So we still have no orbit because we're still on the ground. So we're going to leave this blank. And the maneuver that we're going to perform is called an Earth ascent. And it's very straightforward. All rockets that go that deliver orbital payloads have to do this. It's very straightforward. We're sitting on a runway. We're going to ignite our engines. We're going to take off. We're going to fly like an airplane. We're going to nose high up into the atmosphere. We're going to get higher through the stratosphere, into the mesosphere, and climbing through the thermosphere. And finally, we will reach a point where we can perform main engine cutoff. And that's the end of Earth ascent. Again, I'm going to calculate this later. And just note that every time the main engines are opened, an entry must be made in the table. So that's been acknowledged. I'm going to clear it. Okay, so we're sitting in Earth orbit now. Right? So, well, actually not quite. Right? I said we're going to make a main engine cutoff. And then we're going to do... Whoops, I didn't change the phase here. Still on Earth to low Saturnian orbit. This time our orbit is sub-Leo. Because we've just done main engine cutoff, so we're technically in an orbit, but we're not going to stay that way. So, at the very top of our swing, the apogee, we're going to perform Earth, Leo. Well, actually, Earth is contained in Leo. Leo circularization, right? So now we're in a parking orbit to stay. We're safe. So for the phase, that's just a note to populate from this section above. In the orbit, we're going to get from the timetable below. Although I think I'm going to change that order. Let's see, this is the timetable. And this orbit timetable will be filled out in the 8th step, so we can skip it for now. So we're going to actually populate it based on this other section. So we'll clear that. We're still on Earth to low Saturnian orbit. We're now Leo circularized. So that means we're in a Leo orbit. And then we need to perform the next maneuver. Okay, so now what needs to happen is our circular orbit needs to be changed to coincide with the sun's, roughly the sun's equator, or the orbital plane of the planets, more relevantly. So in order to do that, we're going to need to do what's called a plane change. So we're going to do a plane change, which will get us aligned with the path of Saturn. Okay. And yep, that was the one note that I made when I changed the process. So it avoids the danger zone and saves fuel. So we're going to skip the Saturn deep dive. Clear that. Still on Earth to low Saturnian orbit. We're still on Leo. So now what we've got is a low Earth orbit. We're orbiting the Earth, and we're orbiting the Earth in a plane that's aligned with the planets. So what's next is to break away from the Earth, right? So now we're going to do the Saturn transfer injection. This is a big one. So we talk about like major maneuvers. The first major is Earth ascent. The next major is Saturn transfer injection. You might also think of them as critical. If we do half a plane change, it's okay. If we do half a Leo circularization, it's not preferred, but it's survivable. If we do half a Saturnian injection, it's really bad. It's loss of mission. And if we really mess up, it could be loss of crew and vehicle, which we really don't want, obviously. So then what's going to happen is we're now on an orbit called Trans-Saturnian Orbit. Sorry, STO. Got it backwards. Saturnian Transfer Orbit. So now we have broken free of the Earth. We're flying through the solar system on a larger scale. We're climbing slowly past into orbits of Mars, Jupiter, etc. And as we do that, Mars and Jupiter, as well as every other planet in the solar system, is going to tug on the orbit in various which ways that were unknown, as well as the radiation shining on the craft will cause the orbit to perturb. Sometimes gases will come out of the ship and cause various perturbations. So we need to do a mid-course correction maneuver, which I call an MCC. So we're going to do an MCC to fix any possible perturbations. As a matter of fact, based on the results from the mission to planet Uranus, I now need 3 MCCs. So we're going to do MCC 1, MCC 2, and MCC 3. This is actually something that real missions do in real life. Normally it only takes about 2 mid-course correction maneuvers, but keep in mind that we're using a less rugged planning system. We're not capable of getting the same accuracy that NASA is. So I have a note here, don't forget that Titan will lower hover thrust on engines due to the atmosphere. That's important for later. I'm actually not going to clear that. I'm going to stick it down here towards the bottom. We'll come back to it later because it's not relevant now, but it will be later. Okay, so we're going to clear that. Again, still Earth to low Saturnian orbit. We're still in the Saturnian transfer orbit STO, right? So it's been a few years now, and we're finally getting close to the Saturnian orbit. We're now inbound to Saturn. Saturn's looking like starting to look like a tiny dot out the window instead of a star. It's now got volume to it, right? We're starting to see Titan, the small orange ball, making its rounds around the big gold ball that's Saturn. We can start to see the rings as distinct from the planet, so we're coming in now. So now what we have to do is an arrival inclination burn. We're still on the Earth to low Saturnian orbit phase, still Saturnian transfer orbit, but now what we want to do is we want to make sure that when our path comes in, it's in line with the moons. And the reason we do that is so that we can travel to the moons. So we need to do another plane change. And as a matter of fact, I call this the I think it's called the arrival inc adjustment. Inc short for inclination. Okay, so we've done our arrival inclination adjustment, and we're starting to get really close to Saturn, right? It's starting to look like a big ball, and then we're starting to see some of the other big moons. We're starting to see Rhea, Iapetus. Maybe we can see Enceladus because it's as bright as snow. We're starting to see the atmosphere of Titan. The rings are now completely distinct from Saturn itself. So we're still on Earth to low Saturnian orbit. Now what's going to happen is, remember I said that we're going to drop the probe off. So what needs to happen is a probe release maneuver. So what we're going to do is up until this point, I've just been saying I want to go to Saturn. So I've just tried to get the path as close to Saturn's center as we can. Now, we don't actually want to go into Saturn for obvious reasons. So at this point, what we're going to do is we're going to fire the engines to raise the orbit to the cloud tops of Saturn. The cloud tops are in atmosphere that is sufficiently dense to stop anything going under orbital trajectory. So at this point, we're going to do an EVA. We're going to unpack the probe. We're going to arm the probe. We're going to release it from the craft. Then we're going to ingress back into the vehicle, close up the hatch, and then leave the probe alone. And we're going to adjust our orbit again to the, what I call the haze top. We're going to do the haze top altitude adjustment. So obviously our ship is not built to enter the Saturnian atmosphere. So what we're going to do is we're going to burn the engines again, and this time we're going to raise our altitude of lowest pass from the cloud tops all the way up to the haze tops, which is about 2,000 or 3,000 kilometers above Saturn, perfectly safe for us. So again, Earth to low Saturnian orbit, Saturnian transfer orbit, haze top, altitude adjustment. Okay, now, finally, we start coming through the Saturnian moon orbits. We pass the orbit of, and Saturn is like a solar system in miniature. We pass the orbit of Iapetus, Titan, Rhea, Dione, Tethys, Enceladus, Mimas, and then we start going over the rings, and then we go inside the rings, and then all of a sudden, we turn sideways, and suddenly Saturn's now starting to look flat. That means that it's time finally to leave the Saturnian transfer orbit and get captured by Saturn. So this is the Saturn orbit insertion. So this is where we stop sailing through the solar system and finally say, no, I want to stay at Saturn. We burn our engines, and now we're going to stay circling Saturn. Okay, so this is still Earth to low Saturnian orbit because we haven't begun the process to go to Enceladus now. And once complete, this will put us in low Saturnian orbit. So we've done our orbit insertion. Now we're going to do a circularization for ring avoidance and meeting up with Enceladus. So it's not really a circularization. We'll call it Enceladus sync and ring avoidance. Hopefully that comes out to a really cool acronym. ISARA, the ISARA maneuver. Okay, so now we're still doing Earth to low Saturnian orbit. And now we're finally doing low Saturnian orbit to Enceladus, right? Okay, so we're synced up with Enceladus, but ultimately there's going to be a little bit of plane change error that would have occurred as we performed all of the maneuvers, dropping the probe and capturing, or getting captured by Saturn. So now we need to do a plane change maneuver, right? Enceladus, plane change. We're still in low Saturnian orbit. Actually, I take that back. We're on our way to Enceladus. ETO, Enceladus Transfer Orbit. And let's use lowercase e here because otherwise we're going to end up with an Earth transfer orbit, and that'll be big E. So we don't want to confuse them. So LSO to Enceladus. We're still on an Enceladus transfer orbit. Now we're coming up to Enceladus. We need to slow down to get into orbit. So now we're going to say Enceladus orbit insertion. Okay? So now we're in a circular orbit around the moon Enceladus. So now what's next? Well, this sounds really weird, but for propellant purposes, the columns F through J, I need to have an extra line here because otherwise we would combine the orbit insertion with the landing maneuver, and I definitely don't want to do that. We need to check the we need to check the fuel before we land. So I'm actually going to insert a blank line here. Still LSO to Enceladus. We're no longer in transfer orbit. Now we're in low Enceladus orbit. Okay, and that's it. It's just to put the numbers in here as soon as we finish the previous burn. So, the next thing, still in LSO to Enceladus. We're in low Enceladus orbit. Actually, no, because we're landing. There's actually no orbit because we're changing it the whole time. This is Enceladus landing. Okay? So there's Enceladus landing, and now we need to insert another blank line. Finally, LSO to Enceladus. Landed Enceladus. Right? So now we're actually sitting on the ground of Enceladus. And at this point, in fact earlier, we're going to go to the next stage, Enceladus to Titan. Okay? So we're sitting on the surface here now, and we're going to take off now. So the first thing that we're going to do, Enceladus to Titan, we're going to do Enceladus ascent. Right, so we're going to get into orbit again around Enceladus. Once we get into orbit, we're going to do another plane change. This is low Enceladus orbit. And the reason we're going to do this maneuver is to get rid of any sideways velocity that we might have picked up in the landing process, just because, you know, avoiding cracks or crevices in the ground, asymmetrical thrust, etc. So we're going to do a plane change to line up with Titan. Okay? And now, if you'll imagine Enceladus and Titan as you could imagine Earth and Saturn, after the plane change, we're going to do Titan transfer injection. And now I can look up here and see, let's see, Saturnian transfer injection. That was Leo, so this will be low Enceladus orbit. Whoops, that was the wrong Leo. No, why are you doing that? Okay. And just like before, we're going to need to do MCCs. So we're going to do 2 MCCs because the distances involved are a lot smaller. Okay. And then these are going to be in TTO, Titan Transfer Orbit. Still on the Enceladus to Titan. Okay, and then we have Titan Orbit Insertion. Okay, now is where stuff starts to digress again. So we're going to add another line here. Just like this one. Low Titan orbit. Okay, and now things get a little bit different. So, on an airless world like Enceladus, you have to deorbit and land. Now, Titan actually has a thicker atmosphere than Earth. So, like Earth, we're going to actually do a deorbit maneuver. And landing will actually be occurred using just a little bit of hover thrust, okay? So, still on the Enceladus to Titan leg, still in low Titanian orbit, we're going to do Titan deorbit. This maneuver will put us into the Titanian atmosphere. We will slow down due to drag and begin falling through the atmosphere. We will fly like an airplane. Well, we will glide like an airplane, really like the space shuttle. And when we get close to the surface, we're going to level out, open the hover engine doors, and just before we hit what would be stall speed, we start running the hover engines and the retro rockets, slow down, and touch down on the surface of Titan. Actually, I want the next one, Titan to Iapetus. Alright, landed Titan. Actually, I forgot. There's one more step, right? Because this isn't like Earth. On Earth, you can land on a runway. We can't do that. So Enceladus to Titan, no orbit. This is Titan landing. So basically, we don't need fuel until the very last second, and then it's just a little bit of rockets to stop us. Kind of like how the Curiosity rover and the Perseverance rover landed. Okay, so now we're on Titan. Still no orbit yet. This is Titan Ascent, right? And this one's going to be challenging because when we take off from Enceladus, we add some hover thrust, and then when we get to about 3 kilometers, we jam the throttle full forward, wait until we get into orbit, and shut the engines off. If we did that on Titan, we would be out of fuel because Titan is a very thick atmosphere. So what we actually have to do is fly like an airplane, like we took off from the Earth, climb very high up into the atmosphere at about 45 degrees. And only after about 15 minutes will we be high enough to finally get into orbit around Titan. So that's going to be a little bit interesting and a little bit tricky. In fact, this is going to be the hardest thing to plan mathematically. So then, like we did with Enceladus, we're going to do a Titan plane change to align us back with Saturn's equator. And this one might be a little bit bigger because the winds on Titan has winds. So now we're talking asymmetrical thrust and wind. Titan to Iapetus. This time we're back in low Titanian orbit. Okay. Now we're lined up. We're ready to do our travel to Iapetus. So this is going to be the Iapetus transfer injection. done in low Titan orbit. And again, just like before. And you can see how all of a sudden we've got all these maneuvers, right? And we're going to run out of room. Actually, this is Iapetus Transport Orbit, ITO. MCC1, MCC2. And then we're going to have... And now things are starting to get into the groove. We're going to have Iapetus orbit insertion. So I think what I'm going to do here is move this note over to the planning column, which is this one, estimated meters per second in Titan ascent. That's where that belongs. Okay, so now we're around Iapetus. We're going to insert our orbit line again here. So this is low Iapetus orbit, LIO. Okay, now that's done. So then we're going to do Titan to Iapetus again. We're actually about to leave low Iapetus orbit. And this time I'm going to look up at Enceladus as a verification, because Iapetus is airless like Enceladus and not like Titan. So we're not going to follow the Titan process. So we have Iapetus landing. Then we have our row below. Finally, Iapetus to Earth. Landed Iapetus. Okay, so now we're sitting on the ground at Iapetus. Then we have to take off again. Iapetus ascent. No orbit, but this is the Iapetus to Earth phase. And I'm going to have to add some lines here, so let me go ahead and do that. Okay, so I have needed to add another 8 lines here, and this should be enough. So we had our Iapetus ascent. Now we want to add another blank line for accounting purposes in low Iapetus orbit. Okay. And now we finally break out of our moon visits. Okay, so we did the line there. Now we're doing a maneuver called the Iapetus escape. This is a little bit different. So now what we're doing is we're breaking away from Iapetus and getting into a slightly higher orbit where we will begin planning the trip to Earth. Okay, and now Iapetus is actually pretty high up there, so I think I'm going to actually end up calling this high Saturnian orbit. So we're now in HSO. Now we're going to do a plane change, align to Earth. Okay, so now we've gotten away from the moons. We're sitting there on Saturn. We're starting to get ready to go back to Earth. So what we need to do is we need to adjust our plane so that we're back in the sun's plane that all the planets are in. And at that point, we will be lined up. So now, in high Saturnian orbit, we can finally do our Earth transfer injection. This is probably the most critical burn of them all. And I really mean that. Because if you get this burn wrong, you will not have enough, you won't have enough fuel to get back to Earth. If you go at the wrong time, you might come to the Earth with something like 20 kilometers per second needed to slow down. And if you come at the right time, it's only like 5. So if you plan it right, 5. If you don't show up when you planned it for, 20. And that's a very big problem. That's beyond what my contingency padding can do. So we have to be very careful about that ETI burn. And then something funny goes on with Orbiter. When I came back from Uranus last time, there were a lot of issues with being tugged in every which direction. Now, I don't know if this is Transx just not factoring in non-spherical gravity sources or multiple gravity sources. I'm not sure exactly what happened. But long and short, we had to do so many mid-course corrections that I'm just calling this the MCC bank. It's just a whole load of maneuvers that take place. This time we're using the big E. Nope, the big E. Earth transfer orbit. Okay? And we're just going to say, like, you can use 1,000. And as long as you don't use your entire budget, fire your engine as many times as you want. That's the one time that we're not making an entry into the table. Okay? So now we're finally, Earth is in the window, getting down to Earth. So Iapetus to Earth. Earth, capture and orbit insertion. So now we're back home. We're orbiting a few hundred kilometers above the planet where the ISS orbits. Let's see, Saturnian orbit insertion. Yeah, that's orbit is blank. Okay. So Earth orbit insertion, we're there. And now we're going to insert another blank line for the orbit. Now we're in Leo, big E, for low Earth orbit. Now we're going to maneuver. This maneuver will take place in Leo. This is going to be yeah, let's not say re-entry because our first entry is in Titan. So we're going to say atmospheric entry, planar alignment, right? So we're orbiting the Earth, and at some point we need to get our orbit path to line up with the runway, so that when we come shrieking out of the sky, we're going to be going towards Wallops Island, right? Because we want to land on the same runway and park at the same hangar that we took off from. Okay? So now we're lined up. The last thing that we need to do, Iapetus to Earth. Not in a particular orbit. De-orbit. That's it. So we literally fire our engines just enough to get dragged down by the atmosphere. We come shrieking down through the sky. We get the runway in front of us. We glide down to a landing on the runway. We slow down and we stop. If we are completely out of fuel at that point, it doesn't matter. Because at that point we can call for an airport tug to pull us off of the runway. I plan to taxi back, but that's non-critical fuel. If we run out of fuel at that point, I'm still considering mission success. Because literally all you got to do is just call airport tower and say, hey, can you please tow me off the runway? And yeah, tow you off the runway. That's it. So here are all the maneuvers that we're going to do. And just make sure that we've covered all of our bases. Earth to low Saturnian orbit, low Saturnian orbit to Enceladus, Enceladus to Titan, Titan to Iapetus, Iapetus to Earth. That's it. So in total, We have 47 maneuvers that we need to plan now. Okay, this step should be slightly easier than the previous step, so I was wrong about that. But the hardest part by far is going to be getting this estimated delta V needed for the orbits, or the maneuvers. So what we need to do now is figure out what orbits we want to be in, right? So we're on the ground. That orbit, there's no such thing as it, right? Then we do our Earth ascent and then get into low Earth orbit. So when the low Earth orbit circularization takes place, we're in a suborbital orbit, right? That sounds crazy. So what do we want? We want a LEO in the lowest, and what we're gonna do is we're gonna list what we want the orbits to be, and then we're going to numerically define them. And I'm gonna numerically define them off screen to save time. So I want a low Earth orbit in the lowest ecliptic inclination possible, and I want the apogee, or highest part of the orbit, to be 240 kilometers, and the perigee, or the lowest part of the orbit, to be minus 240 kilometers. Okay? Now we get into low Earth orbit. So what do I want? I want a low Earth orbit in the lowest ecliptic inclination possible, 240 kilometers circular. Okay. Then I want the plane change, right? So, I've done the plane change. Now we're going to go into the Saturnian orbit injection. So now, LEO, no, don't do that. 0 inclination, 240 kilometers circular orbit. And now hopefully this is starting to make a little bit of sense what's going on. Now that we can actually correlate to our maneuvers, what they're doing to the orbits. Okay, so next we're going to do the Saturnian transfer injection. So what's this going to be? This is going to be a ideal Hohmann. It won't be, but we're going to hope that it's going to be. A equals Earth semi-major axis plus Saturn over 2. And that's it. It's not going to change with the mid-course correction maneuvers. Then we have our arrival inclination adjustment. The probe release maneuver. But okay, so by this time we want lowest, and it might not be possible to get to 0, but we want lowest moon inclination possible. Okay, and then we need probe release maneuver. So all we care about here is the periapsis. Periapsis at the cloud tops. And like I said, I'll just make that. I'll make that numerical later. Then we do our haze top altitude adjustment at the haze tops. Okay, and then we do our orbit insertion. That will put periapsis at the haze tops, apoapsis at the orbit of Enceladus. Okay, then we do the plane change, or hang on, we did the sink and ring avoidance maneuver. This is a tricky one, so we'll just say as needed to sync with Enceladus. And I'm pretty sure that Cassini actually flew this way. Cassini was a Saturnian orbiter that was actually sent by NASA. We're going to do a lot of what Cassini did, except for the fact that we're going to be able to land and take off. Cassini did send a probe to land, kind of like what we're sending, an atmospheric probe. But once it landed, it died. It couldn't take off again. And we're going to take off and land and take off multiple times. So, even though it says as needed, and I can't tell you what it's going to be beforehand, that's not necessarily a bad thing. Because I'm going to factor in more fuel and more time than could ever be needed. Okay. Then we do our Enceladus plane change. Then we do inclination 0 to Enceladus. This puts us in line with Enceladus. Then we do our orbit insertion. Then I want a low Enceladus orbit. Now we need to actually look up some scientific information. Okay, so I had to dive really deep for this one. I found a scientific article, the European Planetary Science Congress. These folks in Berlin who had basically said in the very beginning of the abstract that the relief is actually not more than 2 kilometers, which is crazy. So this means we can actually get exceedingly low to Enceladus, but not too low, because Saturn will perturb our orbits. But not too low, because Saturn will perturb our orbits. So now I can define what low Enceladus orbit is. We'll say 20 kilometers. That's as low as we want to get. So then we land. That's no orbit. And then we take off. And then we get back into that same low Enceladus orbit. 20 kilometers. Then we do our plane change. And then we want low Enceladus orbit 20 kilometers, but also aligned plane for Titan. Then we do our Titan transfer orbit, and this is going to be just like the one that we did with Earth and Saturn. Ideal home-in, but this time we're going to use the semi-major axis of Enceladus plus Titan divided by 2. Okay, and that's going to be the same. Then we do our Titan orbit insertion. And this one we're going to have to be really careful about, because Titan has a very thick atmosphere. It has a very high stretching atmosphere. So, let's see. I think I did a couple of tests years ago up to 200 kilometers. I'm going to have to pause and do a little bit of math to figure this one out. Okay, here we go. I did a little bit of quick math to figure out what altitude we need. So what I did was I took the Earth's scale height, which is 8.2 kilometers, and then also calculated Titan's scale height, which is the temperature times the coefficient of air divided by the gravity. So it's 95 degrees above absolute zero. Titan is 95% nitrogen, which is close enough for me to assume is the R value. So I'm using the Earth's, even though it's for Titan, but it should be okay, because again, Titan is 95% nitrogen. And Earth is 75% nitrogen, and then you have oxygen, and on Titan you have methane. So it should work out. Divided by the gravity, 1.35. So I get the scale height. Then I list the Earth's atmospheric density at sea level, Titan's atmospheric density at sea level, and then I say, okay, I'm comfortable orbiting Earth at 120 kilometers. What pressure is that? So then I run the density equation. So that's pressure at sea level times e to the negative current altitude over the scale height, and what we find is that the preferred density for orbit operations in my plane is 5.5 times 10 to the minus 7 kilograms per cubic meter. So then what I do is I turn around the equation and say, okay, now work the equation backwards. I want to know at what altitude Titan is going to be at the same pressure that I orbit in low Earth orbit. So what I did was I did negative scale height times the natural log of the pressure that I want divided by the pressure of Titan at sea level. That gave me the answer of 328 kilometers. And just to be nice and round, we're going to round up to 330 kilometers. And there we go. That's our answer. Our low Titan orbit will be at 330 kilometers. And you can see right here, this is why we add that little orbit line, so we can stick this information in here. So then we do our Titan deorbit, we do our landing, we're landed. Then we take off again and get back into the same orbit. So we want low Titan orbit, 330 kilometers circular. Then we do our plane change, low Titan orbit, 330 kilometers circular, and 0 relative inclination to iapetus. Okay. Then we do our iapetus transfer injection. So let's go back up here to the ideal Hohmann again. And this time it's going to be Titan plus iapetus over 2. Again, that's just dictated by the laws of orbital mechanics. Okay, so then we go all the way up to iapetus. We do the orbit insertion. And let's see where I finally put this in. Oh, that's right. There's no mid-course corrections because we're not going from a moon at that particular point. So I'm trying to figure out where I should put the orbit. One below. On that line. Duh. Okay. Iapetus orbit insertion. So now we got to figure out how high iapetus is. Okay, here we've returned to yet another research paper. Here are the folks that did it. By the way, this is a particularly good one because I recognize this name. I highly recommend you check out the Melody Sheep video called Onward to the Edge, which basically underscores every reason why I love visiting Saturn. There's this one line from Carolyn Porco, which is immortalized, in which she is auto-tuned to sing, "The Saturn system offers splendor beyond compare because of its rings and very diverse moons." So anyway, I just know that she's a very prominent Saturn astronomer. But anyway, we actually have a relief model of iapetus here. And that's a lot higher, right? Negative 12.5 to 32 kilometers. And we want to add in some buffer zone. So we're going to discount the below surface level because we're only concerned with the average. That's what our spaceship or spacecraft computer uses. So we're going to say that the maximum relief is 31.5 kilometers. Well, let's set a 60 kilometer. Yeah, we'll do a 60 kilometer orbit around iapetus. Low iapetus orbit. What did I say? 60 kilometers circular. Okay. So now we're in orbit, then we land, we're on iapetus, we take off again, and now we're back in this orbit again. So low iapetus orbit, 60 kilometers circular. Then we do our escape, and now we got to figure out what orbit we're on. So we're gonna do an orbit to get away from Iapetus, and oh boy, let's say. Well, we know that the periapsis is going to be Iapetus. The apoapsis, Iapetus, let's just generically say times 1.1. That will keep us synchronized out for square root of 1. Actually, no, it would be 2/3 root of 1/10. So basically what that means is it's going to be a long time before we run into Iapetus again. Something like 7 orbits. So that's a safe location to be. Then we do our plane change alignment to Earth. So we do our same strange orbit, which we're going to name a little bit later. And let's see. Periapsis, Iapetus, apoapsis, Iapetus, and planar aligned with Earth, because we're going back. Okay? So then we do our Earth transfer injection. That is this, up here at the top. It is exactly that, because it's the reverse. Okay? So we do our home in Earth plus Saturn over 2. Then we do, let's see, what is this? Earth orbital insertion. Oh, but first we have the the MCC stays blank. That doesn't need an update. And then we're back to Leo. We're going to use the same orbit as before. Leo in the lowest. We don't even have to say that. Actually, yeah, we do. But it's going to be a little bit different. So now we're in Leo. But instead of saying the lowest ecliptic inclination possible, now we're going to state Leo with minimum inclination of 38 degrees. Okay, so then we do our Earth entry planar alignment, and the final orbit that we're going to leave with is low Earth orbit so we'll say low Earth orbit with inclination to cross Walb's flight facility. And that's it. After that point, we hit the D orbit and the orbit falls apart. We land back. So now I'm going to spend the next probably half hour numericizing this entire column into classical orbital elements. Okay, as you can see by the clock at the lower right hand of your screen, you can see this took a lot longer than 30 minutes. But it's all done now, except for one value that I left so that we could do it ourselves. So this should hopefully give you an idea of how I went from these orders to specific numbers. So I asked for a low Iapetus orbit that is 60 kilometers circular. So the first thing that we need to do is figure out what the semi-major axis is going to be. We want a circular orbit, which means that the semi-major axis will be the same as the altitude all times. So when we talk about altitude, to get a semi-major axis, you need the radius of the orbit. That is the radius of the planet plus the altitude. In this case, we're not looking for a planet, we're looking for a moon. And this is the number right here that we are looking at, 734.5. So 734,500 meters. Okay, so now going back here, we want 734,500 meters. and then we want to add on 60 kilometers, so that's 60,000 meters. And so we get 794,500. Going back, we want a circular orbit. The next to fill in is eccentricity, and that determines your shape of the orbit. And a value of 0 is a circle, a value of 1 is a perfect parabola, value of infinite is a line. And I said we wanted a circle, so that's real easy. 0. The next thing we need is inclination. So this has to do with what we're targeting, right? So the next thing that we're going to do is an Iapetus landing. And I said that I wanted to target the dark leading hemisphere of Iapetus. Because it's a hemisphere that I'm targeting, that means I can shoot anywhere between 80 degrees north and 80 degrees south. So the best thing to do from a perspective of maintaining as much velocity as possible, because if you keep everything in the plane, it conserves velocity rather than having to do a plane change up and back. So the most fuel efficient solution is to stay around the equator. So we're going to choose an inclination of 0. The next thing is the right ascension of the ascending node. And because the inclination is irrelevant to us, that also means the right ascension of the ascending node is irrelevant to us. So I put in DC, which means don't care. Now you might see an RT, and that means real time. Here's an example of the inclination from the Iapetus transfer injection. What I'm saying there is whatever inclination works for a encounter, use that, because the moons aren't going to run in a complete plane. Some will run above the plane, others will run below it in inclination. You just have to divvy it up. The numbers are so small here that I'm not really going to worry about exactly what that is. So I'm just going to blanket assign 3 degrees. That's the most it could be. And that's based on the worst case scenario of the two moons being as out of sync as they can be. Okay, anyway, the last thing that we have here is the not true anomaly, the argument of periapsis, which is basically what part of the orbit is the absolute lowest in your orbit. And in that case, we have a circular orbit, which means that's undefined. And because it's undefined, that also inherits the don't care clause. Lastly, we also want to assign, we can get rid of the instruction now because we have converted the instruction into a flyable orbit. So the last is the major body, right? What are these numbers in reference to? 794,500 sorry, that should be meters. An eccentricity of 0, an inclination of 0 to what? To Iapetus. So there we go. And now if I scroll down, you can see we have just about the same numbers. The only difference is we have a don't care for the inclination on the ascent. I think I'm going to change that to say 0. Again, just keeping everything in the plane. And now we're done. Also, in the meantime, when I figured out what you'll notice that I have an inclination selected for Titan. What I did was I decided I wanted to visit a lake, and unfortunately the Titan lakes are very far north and south of the equator, so the closest equator-ward lake there was Cyanoskeg Lacus, which is after Cyanoskeg Loch in Scotland, and so we're gonna go with that as the landing site. So that's pretty cool. We already know where we're going to land On Titan, that should be relatively easy to do based on the extremely dense atmosphere. And now, folks, it is time for the hardest part of the entire mission planning process, solving the maneuvers. This is where we actually start to put numbers on the spreadsheet and say exactly what's going to happen and when and how much. So I'm going to move as fast as I can. I'm going to be, again, this isn't a tutorial, so I'm going to move quick. Hopefully things make sense. I'm going to briefly explain everything, but anyway, here we go. Okay, so for the taxi fuel, this is my old Uranus flight, and you'll see I set an estimated of 500, and then we did an actual of 308. This is variable because we're talking about wheels rolling across a surface. So even though we got 309, I'm going to go with 500 again because we're using a different craft. So there we go. First number going in, 500 for the taxi fuel. And hey, if that's too much, it's the same thing of when I said what happens if we run out of fuel on landing. If we burn too much on the taxi, we'll just get the fuel truck to come onto the runway. Yes, it's a pain in the butt in real life, but I mean, when your life is at stake, I don't see a problem with this. Okay, so the next thing is the Earth ascent. This is a very complicated and challenging process. So I'm actually going to skip this one for now. This is something that is better observed in a test than calculated. And it's easy to fly up into Earth's atmosphere and back. It's not like flying the mission. Now, later on, I think I mentioned the hardest thing is going to be the Titan ascent. That's going to be calculated. I'm not going to do a test because that's not acceptable. That's like cheating, right? You can't measure what Titan's atmosphere is like if you can't reach it in the first place. So we're going to skip this. Well, for now. We'll come back to it. Okay, so the first thing we have is a low Earth orbit circularization. So I happen to have a cheat sheet in front of myself which explains how I solve certain maneuvers. So now I want to do a circularization solve. That's going to use my Vis Viva calculator. So woohoo, you guys get to see the calculator in use for the first time. Okay, here's the Vis Viva calculator. We're actually at the very beginning of the spreadsheet. This is the first equation that I put in. You know, besides, I have this solar system reference card, which contains all the relevant information of the solar system bodies. But anyway, the first calculator is Vis Viva. So all we need is the current radius, the current mass of the planet, and the semi-major axis. So now hopefully it makes a little bit more sense why I start to put those numbers into the orbits. So what we're going to do is we're going to solve a velocity, and that's v1. Then we're going to change it to the new orbit, and that's v2, and then we subtract them to get delta v. And that's how this works. So right now I have the mass of the Earth plugged in, and then we need the semi-major axis. So now we're going to go all the way back to the mission information table, and we need the semi-major axes. This is the only parameter that changes. Circularization will occur at 240 kilometers because circularization needs to occur at apoapsis and periapsis, and periapsis will be under the planet. So we're going to start with a semi-major axis of 6378, which makes sense because that's the major radius of the Earth around the equator. Now the only caveat to that is we have an eccentric orbit, and part of the orbit extends into the Earth. So now We need the second one, which is 6618, and I need the meters on there, so I need to take the three numbers. The next thing I need is the altitude. And because the altitude is the same as the semi-major axis in a circular orbit, that means that we can take the semi-major axis of the second orbit and inherit that as the radial distance in both cases. There we go. Control left click. I always forget that shortcut. Okay, so the semi-major axis 6378000, and the R in both cases is 6618000. Okay, and that looks like a good number. 7,616 meters per second. That's V1. Now, to circularize, we're going to raise the semi-major axis to become the altitude. 6618000. Enter. And now we have 7,760, and I always round up, even if it's 0.014 meters per second. So now, if I subtract those numbers out, and of course I can't do this in my head. If I subtract those numbers out, we're going to go over to right here, Leo circularization. 7764 minus 7616. Boom, 148 meters per second to circularize. And now we have that taken care of. Okay, the next thing we have is a plane change. So, if you take a look here, we want to get into the ecliptic. We're taking off with an inclination of 38 degrees. That's the laws of orbital mechanics, because we are at Wallup's flight facility. We're not within the Tropic of Cancer to the Tropic of Capricorn. So that means that no matter what time of day we fly, there will have to be a relative inclination burn done. So if we take off at the right time of day, we can get a minimum of your latitude minus the nearest tropic. Or a cheat way of describing it is the altitude of the sun at noon during the height, or I should say the summer solstice. So for Washington, D.C., for instance, the highest the sun ever gets is 75 degrees, right? So now if we do 75 minus 90, we'll find that the difference is 15 degrees. So that's the actual relative inclination. Now, the reason that it doesn't matter per the time of year is because that 75 degrees of the ecliptic will walk around the day. So it'll depend on the time of day or night that we fly at. And what that means is that just the sun will never achieve height. But have you noticed that during the middle of winter, the moon can be very, very high up in the sky? That's why, is because that same 75 degrees is there, it just walks around. Okay, so now to figure this out, we just need to subtract the latitude minus the tropic and round. So we get 14.55, so we'll round to 14.55. No, we should be able to get that spot on. Actually, no. There's going to be a little bit of difference during the ascent. So we'll round that to 15 degrees. Okay. So I have a 15 degree plane change that I want to do. Now I need to find the plane change delta V. There it is. And here we go again. We're in a circular orbit, 6618000, 6618000. Okay? and that's plugged in for Uranus. We need to change that to Earth, so that's 5.98 times 10 to the 24th kilograms, and we have a relative inclination difference of 15 degrees. Enter. We need 2,027 meters per second, and doesn't that sound large? Yes. That's why everyone takes off from Cape Canaveral. I'm crazy enough to take off from Wallops Island because I'm fantasizing about the far future. 2,027 meters per second. Done. Moving right along. Next is the Saturn transfer injection. Now, I mentioned that this was a big one. It is not anywhere near as complicated, though, as the Earth ascent. So we can actually do this. And the neat thing is we will actually get another number at the same time that we run this calculator. So let's see, we actually want the patched conic. So we're going from Earth to Saturn, which means the parent of both Earth and Saturn is the Sun. So I put the Sun's mass in. Then we have the departure semi-major axis, so I put the semi-major axis of the Earth in. And we're right about average distance right now, so we'll leave it right at 1 AU. Then we put the mass of the departure body, which is Earth, in. The radius of the departure parking orbit in meters. So the final departure orbit will be 6618. That's correct. Now our arrival semi-major axis, that's the semi-major axis of Saturn, which is about 9.8 AU. But I'm using the 10 AU just as a precautionary method. We're just going to say that Saturn is as far away as possible. This is something that I could really look up if I really wanted to and get super accurate, but doing this method is not really accurate to sub-percentage, so I'm not going to try doing this. If I was using an enterprise solution, I could probably get away with doing this, but or get away with actually measuring out where Saturn is, but we're going to assume it's in the worst position. Then I put in Saturn's mass and the radius of my arrival parking orbit. So, I think one of the things that I did in the orbits was actually determining, here we go, the proper periapsis altitudes to target. I did so because I did a deep dive with the Uranus mission, so I had some calculations down here for determining what various densities were at certain altitudes. So we're targeting 200 kilometers for the release of the probe. That will put it in, assuming that it takes a straight path with no drag, which of course it wouldn't. Assume that there would be a static pressure of 25 kilopascals, which is huge. That is basically as dense as the Earth's atmosphere is, around 40,000 feet. So that's going to massively cause a slowdown from orbital velocities and capture it. On the other hand, we are going to fly safely above the atmosphere at 1,433 kilometers. And our instruments should detect an atmosphere, but we shouldn't have any issues with it. I'm really hoping not, because we have to turn retrograde and fire our engines. So we needed 1433, and then we had to add that on to the radius of Saturn. So I had measured it 58,330, and then added on 1333. That gets us 59,663 kilometers. So let's go back to our patched conic. 59,663, and this is kilometers. So we need to add 3 zeros. Okay, so now we've got our final numbers here. That doesn't look right for the first... yeah, the departure semi-major axis is larger than the arrival semi-major axis. There's a mistake here. 149.5 e to the 9. There we go. That looks better. I was going to say, we should expect somewhere around 8 kilometers per second. So there's actually two numbers. I'm going to write them down. 7364 and 10, and of course my pen just gave out. 10,844. So now we come back to the information table, and let's see, we wanted the Saturn transfer injection. That was 7364. But not only that, we also get the Saturn insertion, Saturn orbit insertion number. That is 10,844. So now we've just solved two numbers at once. And the nice thing is we're coming up to the MCCs. And those are pretty easy because they're numerically based. So what I'm going to do here is just use the outbound values that I calculated for Uranus. They were actually quite accurate. Okay, there we go. MCC1, 1019. MCC2, 350. MCC3, 100. Now, the next thing is the arrival inclination adjustment. For that, we want to go back to our plane change delta V. And this one's going to be a little bit tricky because we're going to be coming in with a very high semi-major axis. We also need to determine exactly where we do that. So let me go ahead and put together a few things off screen. Okay guys, I think I solved it. You ready for this? Because it was a little bit unconventional in how I did it. So if we go over to the Vis Viva, what I did was I knew what my velocity would be because I had calculated the patched conic. Once I decided what my minimum altitude was, I was able to calculate the burn needed using the patched conic to bring you to a circular orbital velocity. And that itself was calculated using the relation of square root GM over R. So all I had to do was add the two to get the final velocity. And now that I knew that this number needed to be 36,043, I knew my altitude to begin with. That's what started the whole thing off. I know the mass of Saturn. So then all I need to do is just play around with the semi-major axis until I get that number of velocity to show up. Now, this is a little bit tricky. It's not like normal semi-major axis where you can just use apogee and perigee, because we'll be coming in hyperbolic, which means there is no apogee. So we have a negative semi-major axis when it comes in, and it's not straightforward. So using that, I came over to my plane change delta V calculator, plugged in the semi-major axis, decided that we're going to do the burn, and I do need to amend the orbit plan to let me know, hey, this needs to happen at 7 gigameters, which is approximately twice Iapetus's orbit. Okay, and then I plug in the mass of Saturn, and then I say, well, what is the dimension of Saturn at that point? And so it turns out that Saturn is half a degree wide at 7 gigameters. So I figured, hey, this is a vector problem. All I need to figure out to do is to change my velocity by 1 degree. It's not a typical plane change delta V. Like, for example, if I put in 15 degrees, which is what I might have to do, it's going to tell you that you need 1650 meters per second, but that's just not true because we're at such a great distance. So what I did was took that relation and say, hey, I know these values. This velocity is 6322. This velocity is 6322. All I'm doing is changing this angle by 1 degree. So I had an SAS triangle and then solved the SAS triangle to find the third side. And what I found was 110.38, which rounds to 111. So there we go. A velocity change of 111 outward will allow us to change the plane of the orbit by 1 degree. Or I'm sorry, change the velocity vector by 1 degree, or the relative inclination by 180 degrees. So we go back to the information table, and this value is now 111. And that should account for all cases. I think I counted for about 15 degrees. If that was really the case, and we were planning it to be spot on to begin with, which it usually isn't. Usually what happens is, I said I target the center of Saturn. I think we're going to spend about 55 meters per second. That's what I think. But I haven't developed a real true method to this madness yet. So I've been using big numbers and been cutting down to smaller numbers. So we'll pretend like it's going to be 111, and hopefully it ends up being 55. If it's 55, then my theory is correct. So that's correct. Let's see. Then we have the probe release maneuver and the haze top altitude adjustment. Okay, that's just more SAS triangle solving, so let me take care of that. Okay, so check this out. I have put these numbers into a small calculator in the highlighted area. Only these 3 numbers are what's important right now. So to do this, we're going to assume that it's going to occur at the exact same altitude. So now what we want to do is we want to, say, go from the center of Saturn outwards, because we'll be targeting the center. So we'll change the relative inclination and then move out from the center. It's wasting a little bit of fuel by doing this, but it's making the calculations a little bit easier and manageable. So let's see. I have that set to the periapsis altitude, so I need to subtract. We need to go to 58, and then 230. So basically what I'm saying now is how much velocity change is that going to cost us? Okay, so I got 52.5 meters per second. That's what it's going to take to go from the center of Saturn to the deep atmosphere where we're going to release the probe. So to take our velocity vector from the deep atmosphere to just above the haze tops, or from the cloud tops to the haze tops, what I want to do now is just take the difference, which is we said 1433 kilometers from the 1 bar line, and subtract 200 kilometers from that. So then all we need is 1233 kilometers. So this entire relation becomes 1233. And that's it. 1 meter per second. Again, round up to the whole So we say 2 meters per second. And that doesn't surprise me at all, because that far out, that kind of velocity change would drastically affect the orbit. There we go. So we're all ready to the Enceladus synchronization and ring avoidance maneuver. What was that called again? ESSERA. Also, if you were wondering, the reason that the book is as big as it is because when I solve one calculation, and I believe it to be right, it goes into the book. So I just created a new calculator over the last couple minutes to document this, so that it should be very easy to continue this going forward, which we'll have to do. Just when you think you're further ahead than you did, I found another mistake. You see this burn to 10,844? What that means is the amount of burn required to produce a circular orbit, which we don't want to do. We actually want to produce an orbit that is oval shaped with the periapsis low, but the apoapsis where Enceladus is. So we got to go back to the vis-viva equation, and we know that our incoming velocity is going to be 36,044. That's guaranteed. So now what we need to do is we need to change our semi-major axis to what we found on here for the orbit. Let's see, that's the transfer. That's the one we want. 1.49 times 10 to the 8th. So go back to vis-viva. That's correct. Okay, 1.49 times 10 to the 8th. That is 31,870. That's much more manageable. That's a burn of 4,174. Let me just confirm this against my previous flight. Okay, so I solved the ESSERA burn. It was a little bit more difficult than I thought. The way I did this was I went to my orbital timing calculator and calculated that the arrival orbit will be in that swings between the haze tops and Enceladus's orbit will last 7.5 hours. And in that time, dividing it into Enceladus's orbit, it'll make we'll make 4.3 orbits for Enceladus going around once. So what I did was I said, okay, well, instead of 4.3, how about 3.3, right? That gives us an entire orbit sync worth of time. At some point during that 360 degrees, we would be seeing Enceladus. So what I did was I took a look at the t squared to a cubed relationship. T squared is proportional to the semi-major axis cubed. So what I did was I said, okay, what time will let us go around at like 3.3 or whatever it was, and it turned out to be a 9.7 hour orbit. So I said, okay, 9.7 hours over 7.5 hours squared is going to be directly proportional to a cubed. So I solve that out, and then I get a new semi-major axis that is 1.1879 times the original semi-major axis in the orbit. So then if I raise only the periapsis, that changes the orbit. So we actually have a new orbit that's come onto the scene. This one has a periapsis of 116,343 kilometers. And when I work that out with the vis-viva equation, If I plug in the arrival orbit, we had 7972, and then if I plug in the new semi-major axis, which is like 1.77 times 10 to the 8th, we get 10,187 meters per second. So if we subtract the two, that's how we get to 2214. So that one is done. Okay, so the next thing we need to calculate is the Enceladus plane change delta V. This one's going to be a lot easier. So we take the semi-major axis and write that down. That's going to be 1.77 times 10 to the 8th. And, oh yeah, the median altitude. Well, naturally the radius has to be the altitude, so that should be okay. The semi-major axis radius. Where is this thing? There it is. So we're going to go into the plane change delta V. The semi-major axis is now 1.77 times 10 to the 8th. We don't know what altitude we're going to be making the plane change at, but because there are two nodes, one of them has to be closer to the top than the other. So it would be a safe assumption to assume the semi-major axis as our radius, believe it or not. Because as a worst case scenario, the ascending and descending nodes will lie exactly halfway. Actually, wait a minute. No, as a worst case scenario, they'll be lying at the semi-lattice rectum. Alright, more calculations. And just because you probably thought I was joking. Nope, it's a real thing. So, we have C equals semi-major axis times eccentricity. P equals semi-major axis divided by eccentricity minus C. And the semi-lattice rectum equals P times eccentricity. Okay, and here they are. The number 1.56 times 10 to the 8th. Now we can plug this into the plane change calculator. Okay, here we go. 1.56 times 10 to the 8th as now our altitude. Then we have the mass of Saturn. That is correct. And we are budgeting, I believe it is 3 degrees. Yes. Actually, I had a note to allow 15 degrees relative inclination difference. And this is in the event that Saturn is a little bit edge on and we're not able to eliminate the relative inclination difference. That brings us to 4303. And then for Enceladus orbit insertion, we're going to go back to the patched conic, and this time we're going to use a parent that is Saturn. So Saturn's mass is 5.68 times 10 to the 26 kilograms. Now, because we're departing from an arbitrary location, we won't have to change the mass and radius of the departure parking orbits, but we do have to change the departure semi-major axis. which is going to be, if we go back to the information table, 116,343. This sets up the approach. So 116,343,000. We can leave that alone. We can leave this alone. Then we have the arrival location of Enceladus, which is 238,400 kilometers. The mass of the arrival body, and this is going to force me to look things up again. The mass of Enceladus is 1.08 times 10 to the 20. 1.08 times 10 to the 20th kilograms. And the radius of the arrival parking orbit, we get that from here. That was 269 kilometers. 269,000. And that's the number we want right there, 2245. So for insertion, 2245 meters per second. Okay, this is an orbit line. Nothing happens here. So we're going to leave this blank. And now we're on to the Enceladus landing. Okay, so this next parameter for Enceladus landing, I'm only going to show once. We'll show the Titan landing, but I'll skip the Iapetus landing to keep things moving along. So the way we're going to calculate this is basically we have to kill our orbital velocity that we're going around the planet with. And then once we do that, we'll begin accelerating. And we need to figure out what the speed is at the surface. So the formula here is going to be our potential energy when we kill off the speed, as well as our kinetic from the speed. And what I'm going to do is I'm going to convert both, or rather convert the potential into a kinetic speed so that we can determine exactly what the velocity is that we have to kill. And then we'll add about 1.1% for contingency, just because I don't like to be taking chances with this one. Okay, so the information that I need is the radius of our orbit, which is 269 kilometers. And the other thing I need is the mass of Enceladus. So that's 1.08 times 10 to the 20th kilograms. Okay, so to get our speed, and hence our kinetic energy, what we're going to do is do the GM over R relation. So square root mass of Enceladus times the big G gravitational constant, and then divide by the size of the orbit, which is 269 kilometers. Okay, and what we get is our velocity initially that we're going to have to kill is 164 meters per second. Very slow orbital speed for such a small moon. So what we're going to do is we're going to decelerate, and then we're going to start picking up speed as we begin falling to the surface. So to determine what kind of speed we're going to end up with, we need to calculate little g, which is the gravitation or gravitational force on Enceladus. So we need GM over the radius of Enceladus squared. So let's see, we have the big G, and then we have the mass of Enceladus. We'll need the radius of Enceladus, and that's 249 kilometers because we're in a 20 kilometer orbit, and we square that, so we get 0.11 meters per second squared. That looks good. So now what we need to do is calculate potential energy, which is mgh. Now we can ignore m because we'll have the same n or m rather with the potential energy as the kinetic energy. So we can just do GH. So we're going to multiply that by the h, which is 20 kilometers. That's how far we have to fall. And what we get is 2,323 joules times the mass. So now what I do is I reverse engineer the kinetic energy equation, which is 1/2 mass times the velocity squared. Mass is 1, so we can basically say it's 1/2 v squared. And if I solve, square root of 2 times the energy will give us the velocity. And so I get 69 meters per second. So we add this value to that value, and we get a grand total of 232 meters per second. And that's the landing velocity. 232. Okay, so to calculate the ascent velocity, we're going to take the descent velocity, which is 232. But then we're also going to add in the fact that we are facing up against Enceladus's gravity. So now what I need to do is multiply the gravity times the amount of time that it's going to take to get into Enceladus orbit. Because we're only talking a few hundred meters per second, we can go ahead and assume that it's roughly 30 seconds. So we'll just add another 4 meters per second onto that. So this value will be 236 meters per second. Okay, and then we've got a plane change. This one should be really easy. We're basically counting 3 degrees relative inclination difference. So I'm going to put in the mass of Enceladus here, and our semi-major axis will be the same as the altitude, which is 269,000 meters, 269 kilometers. We're in a circular orbit, and it's just 9 meters per second. It's really easy to fly around a small moon. That's it, just 9. Alright, so the next thing is the Titan transfer injection. And for this, we're going to go back to the patched conic. So now we should be able to borrow a couple numbers here. So 238,400 kilometers is our departure semi-major axis. And then we have the mass of the departure body, which is Enceladus. And let's go ahead and check. Yes, that's the mass of Saturn, so we're good there. The radius of the departure parking orbit we're going to get from down here. 269 kilometers. Okay, and now what we need to do is we need to get the semi-major axis of Titan. Okay, and that is 1,222,870. All right, here we go. 1,222,187. 000. Okay, and then the mass of Titan, which is 1.345 times 10 to the 23rd kilograms. It's a lot bigger. And then the radius of the parking orbit that we decided on, and I think that was 330 kilometers. Oh, but we need the radius of the orbit, so that's going to be 2905 kilometers. .2905 kilometers. Okay, and we are getting into circular orbits, so unlike what we did with Saturn, these numbers will be good. So, burn 1, that is the Enceladus escape maneuver, 3,551 meters per second. The arrival burn at Titan, 1,688 meters per second. So here we go. Titan transfer injection. $3,551. And Titan orbit insertion, 1,688 meters per second. Okay, and the mid-course corrections are actually really easy. In around a planet, basically what I do is I divide by 10 and then divide by 10 again. So this is going to be this value over 10, so 355 meters per second. And then mid-course correction number 2 will be 1/10 of that, or 36 meters per second. So then we have our Titan orbit insertion, and then we have a Titan D orbit. So now we actually need to figure out a orbit that will allow us to perform a re-entry. So I'm actually going to think about that for a little bit. Okay, I finally decided to exercise my orbital re-entry calculator. So basically what I did is I put in our apogee that we're going to be at, the radius of Titan, some other information about it, and the interface altitude is about 150 kilometers, so re-entry will begin roughly here between 53 and 54 degrees ahead with a flight path angle of about 7 degrees. With an atmosphere this dense, that's acceptable. That would be suicidal on Earth and very, very, very much worse on a super Earth or gas giant, but this is acceptable because of how dense the Titanian atmosphere is. So that is what we will use for the orbit. So it's with an apogee of 330 kilometers, an eccentricity of 0.14, so we can actually get our perigee if we go 180 degrees ahead. Our perigee will be negative 383 468 kilometers. So from that we can calculate our semi-major axis. Okay, just to briefly show this, we're going to put our orbit in. So we have Titan, and then we need our semi-major axis. So we can do that by adding the apogee and the perigee and dividing by 2. And this is what they are in terms of planet radius. Okay, so this is our new semi-major axis. Then we have an eccentricity. Taking that straight from the calculator, we know it's 0.14. And the inclination is going to stay at 42 degrees. The right ascension of the ascending node and true anomaly are going to be real time, because we are actually targeting Sionisceg, so we need to make sure that we have the correct ejection orientation. So now we're going to go back to the vis vifa and use both of those values. So we're going from a semi-major axis of 2905 kilometers down to one of 2543 kilometers, and we'll round down for safety. So here we're going to put the massive Titan in. Okay, then we have the semi-major axis, which is, to begin with, 2905 kilometers. And then we have the altitude, which will always be 2905 since we're doing the burn there, kilometers. Okay, so the velocity that we're going to start with is 1,757 meters per second. Now, we're going to lower the orbit to 2,543 kilometers. And now we have 1627 kilometers. So if we subtract, we get 130 meters per second. So Titan deorbit 130 meters per second. Okay, the last thing that we're going to need to do before landing on Titan is obviously the final landing burn. So I know from how much easier it is to fly on Titan, it's something like 45 times easier. Yeah, it's 45 times easier to fly. So if I do a square root of 45, then I can get a fraction slower speed, right? So the minimum safe speed in a fully loaded XR2 is roughly 167 meters per second. So if I do 160, and then divide that by 6.7, then we get our minimum landing speed. So, and that's counting in some thrust. So we can round up and say that we're going to be going approximately 30 meters per second to slow down. And for the retro rockets, that's going to take approximately 10 seconds to slow us down. So we're going to have to add in 10 times the gravity of Titan to accomplish that. And then we're going to have to add the height, which is going to be g times h, to determine the speed that we would gain upon lowering to the ground. And then add a fudge factor of 1.1. Calculating everything out, it comes to 123 meters per second. Okay, next is Titan ascent. We're going to skip that for now. That is the hardest thing to calculate. Then we have our Titan plane change, and that is fairly straightforward. Let's go back to our plane change delta V here, and then we change our semi-major axis to the parking orbit, 2905 kilometers. And then we're going to put in the mass of Titan, 1.345 times 10 to the 23rd kilograms. And then our relative inclination difference is still 3 degrees. So Titan is a much bigger moon. So you can see it's 92 meters per second. That's a lot bigger than Enceladus. So we'll put 92 for the plane change. Then we have the Iapetus transfer injection. And this part is actually pretty easy. This is just the patched conic again. So I said I was going to skip this, so we'll go ahead and come back for the numbers. Okay, so we have the numbers now. The first burn is going to be 1,015 meters per second. The second burn is going to be 692 meters per second. Dividing by 10, mid-course correction is 102 meters per second. And the second mid-course correction is going to be 11 meters per second. And that's it. So now we're on to the Iapetus landing, and it's going to be calculated exactly the same way that we calculated the Enceladus landing. So I will again do this off screen. Okay, for this next burn, the Iapetus escape, this is going to be the reverse of what we did with the Enceladus sink up. So what we need to do now is figure out what the escape orbit is going to look like. Okay, so that's going to be having a apogee of 3.917 gigameters and a perigee of Iapetus's orbit, which is 3.561 gigameters. And this should be stable for a very long period of time because Iapetus takes 79 days to orbit. And our orbit is going to be roughly 10% 10% longer than Iapetus's. So we're stable for about 9 times that, or about 600 days. So we are actually going to be stable for over a year in that orbit, and that's very intentional. So now what we're going to do is we're going to go down to the patched conic and confirm that we have Saturn here. Then we want the departure parking orbit of, or no, not the departure parking orbit, the orbit of Iapetus, right? So that's this one. Okay, and then we need the mass of the departure body. That's what Iapetus is. 1.805 times 10 to the 21. And then we need the radius of the parking orbit. That is 794,500. Okay, and then we need the arrival semi-major axis. That's going to be the apogee, 3.917 times 10 to the 9th meters. And then we need the mass. Actually, we don't need the mass because we're targeting a generic point in space. So there's no second burn. There's only one burn. And then we have the radius of the arrival parking orbit, which is right here. And that, again, is irrelevant. So we're only interested in the first burn, which is 167 meters per second. A Hohmann, you ask? Only 167 meters per second? This is why we start low and climb up, where the numbers start high, many thousands of meters per second, and then there's less and less and less. Except for the Earth orbit insertion. This is a big one. Okay, then we have a plane change alignment for Earth. And that's going to be based on Saturn's right ascension to the ascending node. So I'm going to have to go off screen and conceptualize for a little bit about this. I just realized this one is really simple. all we got to do is just reverse engineer the first plane change, which is this one right here. And I think I was budgeting 15 degrees, but we can check that real quick. I'm going to do that. Okay, so I have confirmed that is exactly what I did. We're doing a relative inclination difference of 15 degrees. So now what I need to do again is calculate the location of the new semi-lattice rectum, and then from that value I'll get a new radius, and we know what our semi-major axis is based on the orbit that we just designed. Okay, here we go. So it took 15 degrees to get into the Saturn system. It's going to take 15 degrees to get out of the Saturn system and address the sun. The mass of Saturn doesn't change. What does change is the radius. We're going to use the new semi-lattice rectum, which is 3.73 gigameters. And we're going to use the new semi-major axis, which is 3.74 gigameters. And this gives us a delta V required 833 meters per second. And we're going to round up to 834. So that's much smaller, thank goodness. Again, totally intentional, right? To get in, it took 4303. And now to get out, it's only going to take 834. So that's why I like to do that. All right, and then here we go, Earth transfer injection. So at this point, we can begin to discuss exactly where, or exactly how we're going to get back to the Earth. Now, I do have to think about what values that I want to use in the parking orbit, because we're in an oval orbit. So I have to figure out what the worst case scenario is and then work with that. Okay, here we go. Mass of the sun, 1.99 times 10 to the 30. Then we have the departure radius. This is going to be 1515 times 10 to the 9th meters. Yes, that's correct. And then the mass of the departure body, this is Saturn itself, 5.68 times 10 to the 26 kilograms. Then we have the mass of the radius of the departure parking orbit. I've already plugged in the low perigee value, and I'm going to bet this is probably the better place to do it because of what's known as the Oberth effect, but we're going to test it. Then we have the arrival semi-major axis, which is going to be the Earth. Now, this time we don't know where the Earth is going to be in its orbit. So we need to get the Earth's perihelion and use that instead. 147.095. 147.095 times 10 to the 9th. And then mass of the arrival body, that's the mass of the Earth, 5.98 times 10 to the 24th kilograms. And the radius of the departure, or the parking orbit, is the same as before, 6618 kilometers. Okay, so to start, we have 3858, and now let's see what happens if I do 3.917 times 10 to the 9th, and see what happens. 3871, 3857. Okay, so as suspected, if we go at the lowest point of the orbit due to the Oberth effect, we're going to end up burning less. So that's going to be the way to do it. That also means that Iapetus will dictate exactly when we detach, because we want to enter that orbit as soon as Iapetus is aligned with Saturn's retrograde velocity vector. So basically when Iapetus is going the opposite direction that Saturn is going around the sun, we detach, we'll fly a little bit higher, Then we'll come back down low again and burn out. That's how that works. So now I've got the numbers. I've got 3858 and 7442. Remember I said that number would be big? Let me get those numbers written down so I don't have to come back here again. And we've got them back in. So here we've got 3858 and MCC, we'll skip that for now, and the second burn 7442. Okay, so this massive MCC bank that I was talking about, let me show you what happened last time. Okay, here is the Uranus flight, and if I go back to the MCCs, I originally planned 3 MCCs. Planned 100, got 100. I thought, okay. I planned another 100 and got 33. I'm like, that's totally okay. But I did not plan an MCC3. And there was 677 meters per second left over. So I'm not sure what the heck happened, but I noticed that there is a consistent perturbation present, and I did 1, 2, 3, 4, 5, 8, 9, 10 MCCs to do that. So altogether, we need to add these 3 values, and we're just going to accept that as the value we're going to use. So I think that was 812, and I think I said totaling 812. I complained about it somewhere and said, hey, there were 10 MCCs resulting in 812 meters per second. Oh, okay, here it is. I stuck it in the Saturn thing. It's right here. So you know when you'll need 812 meters per second in MCCs. So here we go, 812. Because I'm not sure what mathematically is going on, and if I don't understand it, I should replicate it. And because we're going less distance, there is less time for the perturbations to take effect, which means that it's probably less than 812 because we're coming back from Saturn instead of Uranus, but I'm playing it safe. Okay, then we've got the atmospheric entry planar alignment. This is really easy. All we got to do is go back to the plane change delta V, and we're in a circular orbit around Earth, which I should be able to pull from the patched conic. And I forgot what the Hohmann does. Oh yeah, that's just the that's just half the Viz FIFA. Anyway, the altitude. Oh yeah, 6618 kilometers. So 6618000 in both cases, because we're in a circular orbit, the mass of the Earth, and the relative inclination difference. Wait a minute. I said this was easy. How did I think I knew what the... Oh, atmospheric entry planar alignment. Yes, this is easy. It is a maximum of 7.5 degrees. This is just so that the Earth will rotate under the orbit at 15 degrees per hour, or 15 degrees per... Yeah, 15 degrees per hour, and we're in a 90-minute orbit, which means each orbit will appear 22.5 degrees behind the last. So yeah, we need 22.5 divided by 2. So basically what I'm doing is I'm saying, okay, well, at our closest re-entry corridor, we might be up to 22.5 over 2 from it. So that's 11.75. No, 11.5 would be 23. 11.25, 22.5 over 2. that the relation that I wanted? Yes, it was. Okay. So the last burn, 1521. 1521. Okay, and the last one, the deorbit, isn't as crazy as you would think, so we can go ahead and attack that now. It's a big one, but it's not too crazy. Okay, so we want the deorbit, so what we need to do is we need to go back to the reentry solver, and let's go all the way up to the top. The apogee around the Earth is, we're going to 240 kilometer orbit. The planet radius is 6,378 thousand kilometers. Interface is 100 kilometers. That's the Armstrong line for the Earth. This is going to be way too high. Let's try 0.03. Our inclination is going to be averaging 38 degrees, so we can use that. Either it's going, wait a minute, no it's not. It's going to average between 38 and 11.5 plus 38. So that's 49.5 to 38. So we can say 5 more. So we'll say averaging 43 degrees. And then our argument of perigee, this affects exactly where in the orbit the lowest point of it is. This should be, let me think about this. An argument of perigee, we're going to be going over the base near the northernmost extent of the orbit. So that means that the argument of perigee should be somewhere around 90 degrees. No, 270 degrees. Because it would be 90 degrees before the perigee is approximately where we would be performing this burn. Okay, and then true anomaly, we'll just assume that we're going to do it at the top of the orbit, and then the rotational period of the Earth, 86,400 seconds, and the planet mass, 5.98 times 10 to the 24th kilograms. So now, what we want to do is we want to look down here at the 100 kilometer line, which is right here, and take a look at the flight path angle. And that's a very healthy 1.64 degrees. This is an acceptable reentry path, so we can go ahead and use it. So I think I said, yeah, an eccentricity of 0.03. Okay. So, and in fact, if we go down to the 180 degree line, which is right here, we've got our perigee. And that's going to be that line right there. So we knew our apogee was 240 kilometers. Our perigee is going to be negative 145.5 kilometers. And then we add 6,378 to get these in a form that's workable to us. So 6618 is our apogee, and the perigee will be 6378 minus 145.5. $62.32.5. And then from this we can determine our semi-major axis. So the semi-major axis is going to be the radius of the apogee minus the radius of perigee. So that's going to be 6618 minus 6232.5 divided by 6618 RA plus RP, 6232.5. And actually, I just calculated our eccentricity, but that was intentional anyway. The semi-major axis is going to be the apogee plus the perigee over 2. So that's 6618 plus 6232.5 over 2. So that gives us 6,425 kilometers and 250 meters. Okay, so now what am I going to do with that information? I'm going to go to the vis viva equation, and now we're putting in the mass of the Earth, 5.98 times 10 to the 24th, and then our deorbit burn is going to be at the altitude of 240 kilometers, and just because it's bugging me, I'm going to check this, make sure it's 60, yeah, that's right, 6618 kilometers. So that's going to be the same in both cases. And then we need the current location, which in the circular orbit is 6618 with 3 zeros. So our velocity 1 is going to be 7764. And then now we're going to lower the orbit into the atmosphere. That's going to take us down to shucks, I forgot where I found it. Yes, I found it. 6425 250. 6425 250. I have a lot of numbers on my paper now, and I haven't been careful at how I've been putting them down here. 74. I lost it again. Okay, so 7764. We're going down to 7646, and it's appropriate to round down here. So if I quickly do that calculation, we get 118 meters per second. And that's our last burn. And yay, you might say we're done, right? No, because we skipped a few very hard ones, like the Titanian ascent. Is that the only one? No, we also skipped the Earth ascent. So, let's get into how that's done. Okay, so Earth ascent. Real easy, you might think, right? You know, rockets do it all the time, right? Maybe you're really smart and know that it's 17,400 miles per hour. Or maybe you're really, really smart and you know that it's 7,779 or so meters per second, right? So surely that's got to be the number, right? Wrong. The reason it's wrong is because that doesn't factor in the actual amount of fuel used due to a combination of factors such as the fact that you're not accelerating on the ground. You actually have to climb up to about 60 kilometers before you can manage to do that kind of a speed. As well as also noticing that the gases in the atmosphere will cause significant drag, which means that there is going to be wasted potential in the engines that's just going to go out to pushing air out of the way and doesn't necessarily help us. So as a result, because of the complexities of how air flight really works, there's no other way around it. So we're going to have to test it. So how do we test it? Does that mean we have to somehow accumulate all of the drag that occurs? No. What we're going to do is we're going to look at it as an energy perspective. You might remember high school physics and have to be like, okay, well, why do I care about kinetic energy? Why do I care about joules? You know, this kind of thing. No one ever measures the energy content of my car going down a highway. Well, it can be very useful to determine a change in states, and we can actually use it to hack what the delta V would have been in a vacuum. This equation right here is the rocket equation. So there are a number of parameters, and it allows us to solve the delta V, right? So we know what ISP is. That's how strong the engines are. In the case of the XR2 Raven Star, when I test it, it's going to be default ISP 2, which is 2,649.184. Seconds. It's kind of really weird, but ISP is measured in time. And then you multiply that by G naught, which is the Earth's acceleration due to gravity. And it's always G naught. And I know that sounds really weird on Saturn. Why would you ever do that? Well, it's just because rockets took off from Earth. What you could do is relate these two numbers and just say, okay, that's the efficiency of the rocket. You know, just declare this ISP whatever. And that number would be irrelevant of Earth. And then you could divide this by a different G naught and you get a different ISP. But anyway, that's going off on a limb. And then we have that times the natural log of MB and ME. So MB means the mass of the fuel tank at the beginning of the burn, i.e. sitting on the runway, and ME is the mass of the fuel tank when we are past MECO, main engine cutoff. Which means all we have to do is fly a typical ascent in the XR2 Raven Star, note what the tank was before we took off, and note what the tank is at main engine cutoff, and we can solve exactly what this delta V was and use that in our fuel budgeting. So then what I do is once I get this Earth ascent delta V, then I'll introduce a few more equations that relate how the Titanian atmospheric flight differs from Earth atmospheric flight. And we can model the differences and then introduce a number of coefficients to modify that value used to ascend to Earth to ascend to Titan without ever going to Titan in the first place. So that's how we're going to get around the ascent to Titan. So I'm going to pause for a few minutes and do that test off screen. We'll come back for the results. Okay, I have the test results, and I realized that I needed to do two tests because we have a scramjet. The scramjet works in the Earth's atmosphere, and it can help save some energy. However, it will not work in Titan's atmosphere because it doesn't have oxygen. So I had to repeat the test without using the scramjet in order to determine the exact amount of force that it took that we can then extrapolate to Titan. So for the purposes of the Earth ascent, we will use 6,475 meters per second as the delta V, which is less than the orbital velocity because a lot of the heavy lifting is done by the scramjets. And the delta V without using the scramjets is 9,328. And that's what we will be extrapolating for use on Titan. Okay, I have converted the numbers to get the Titan ascent total. So we took the value that we used without the scramjet from Earth, stuck it right here, and then said theoretically we should have been able to use 7,778 meters per second to get into Earth orbit. So then I said, okay, well, how does Earth's atmosphere compare to Titan's? So I needed to put in some crazy calculation called the Earth to Titan integrated atmospheric relation, which is in basically values of density feet or density meters. I know that's really weird to say, but it's kind of like saying, you know, if you imagine yourself as a subway train, how much air and for how long do you have to force in front of you before you're out of it? So I have that equation right here. We have to do it twice, once for Titan and then once for Earth. So basically what I'm saying is here is from the ground to 200 kilometers, which can be assumed to be the atmospheric cutoff for Titan, how much air is there? and how spread out is it? Is it a lot of air over a short distance? Is it a lot of air over a big distance? So the Z1 and the Z2 basically relate the atmospheric thickness to the distance. So I said, okay, the atmosphere that is present on Titan is spread out slightly. Actually, 3 times more than the Earth almost. It has a higher scale height of 20,200 meters. And then I divided that by the Earth scale height of 8,200 meters. So then, once I got that relation, I came back here and said, okay, that value is 0.4581. Then we got this Titan ascent number from the speed in our orbit going circular around Titan, right? So that's just square root of GM over R, so it's 1795. And then lastly, I wanted to add a fudge factor just in case things are incorrect. And then I also needed to add extra delta V to reach 330 kilometers from 200 because we're not, we are not starting, or we're not ending at 200, we're ending at 330, even though the atmosphere ends at 200. So then I said, okay, let's go ahead and calculate this. So I did Earth ascent actual minus Earth ascent hypothetical divided by Earth ascent hypothetical. So I'm getting a relationship between how much extra power we needed to put in for Earth ascent versus Earth in a vacuum. And then divided that by the Titan integrated atmospheric relation to get the total amount of loss that we would expect for our speed. And then multiplied that loss fraction by the Titan ascent velocity to determine the actual amount that we would spend. And then added the, or multiplied the 1.25 fudge factor, and then added the delta V to reach 330 kilometers from 200. That means that we would need 3,261 meters per second. But then we need to add another 20 seconds at 5 meters per second to get us off the ground in the first place, which leaves us with a grand total of 3,361 meters per second, and that's what's going into the spreadsheet. Okay, in checking everything as I typically do, I realized that there was a missing element from the equation. So we need to add the density of Titan's atmosphere and the density of Earth's atmosphere to be precise. So now we're going to say rho 1 is going to be equal to Earth's atmospheric density. Actually, no, that's Titan. And rho 2 is going to be equal to Earth's atmospheric density. So that equals 1.223. This equals 6.13. Okay, so now this is complete. So now coming back here, the coefficients were divided since scale height is on the bottom. And then not only did I divide both, but I also did a square root function because I forgot that density is related to velocity squared. So we get this number. This number now becomes the Earth to Titan integrated atmospheric relation, and the calculations proceed as typical, which means we have a new total of 3,864 meters per second. Hey guys, again, Uh, so you know how I had that little note that said remember to factor in the chamber pressure reduction on Titan? Well, I forgot to do that, but at least I remembered before we took off, right? So there's yet another update. So basically, the way rockets work is they have a combustion chamber, and then they have a nozzle, and then they have an exhaust outlet, and there's an explosion in there, and that explosion occurs at a certain static pressure, and it's actually not surprisingly high. Normally, you think it would be like a pressure front, like what a bomb is, but it's actually not. Um, it runs for the XR2 Raven Star at 4.86 atmospheres, which is actually not that high when you think about it. So this time we have to address the surface pressure, which is a different relationship than the density relationship with the Earth. So on Earth, we have a pressure reduction of 79.2% of what's vacuum, and on Titan we have or sorry, not a reduction. It's a continued efficiency thing. So we're running at 79.2% of vacuum efficiency, and Titan will be running at 0.7 of vacuum efficiency. And unfortunately, the fuel flow is constant, which means that the fuel's going to keep spilling out of the tank at the same rate. So we have a reduction. If I divide the Earth or the Titan reduction by the Earth reduction, then I find that we need to add another fudge factor of dividing by 88% of the total. So if we divide that original total of 3864 by 88%, we have a final number of 4,375 meters per second. So on the ascent, do not forget that Titan will lower thrust on hover engines due to atmosphere. That is now addressed, finally clearing that 4,375 meters per second. And here we go. The entire maneuver plan has been solved. Now, there's a little bit of errors with the with the formulas that I'm going to need to fix shortly, but we can worry about that later. Okay, now that the grueling process of solving the maneuvers is complete, we're finally moving on to the maneuver table summary zone. Did that feel hard and involved? Not to worry. It is, in fact, rocket science. Okay, so now we need a safety margin on the maneuvers that we're going to be doing from the last from the last video where we planned the mission. We were accepting an accuracy of 95.2%, so we're going to put 4.8 in for the time being, and I'm probably going to adjust that because the might have actually been 4.8 before, actually. Nope, it says 5. Okay. I might adjust this later because, as I said before, the reaction control system can cross-feed into the main fuel, and we don't use much of the RCS tank anyway, so we can actually use the RCS tank as a reserve. Okay, then we have a total delta V requirement, and that factors in the safety margin plus the sum of all of the maneuvers that take place. That formula is correct as is. So we have a grand total of 62,584 meters per second of delta V. Why do I say that with such enthusiasm? Consider the following. Okay, when we talk rocket's capability, we use the units of characteristic energy, C3, which is in kilometers squared per second squared. So basically, if I take the entire delta V requirement of the mission and then square it that gives me my C3. But it needs to be in kilometers per second. So we have 62.6 kilometers per second. And if I square that, we get a C3 of 3,906. Our spacecraft is going to weigh approximately 20 tons when empty. So we're asking for a rocket that is delivering to this 20-ton line, where this value reads 3,906. And by the way, this is the SLS, which is going to be the most powerful rocket ever, even more than Saturn V. Although I think it's less than Starship, if I remember correctly. But this basically gives you an idea of just how insanely far in the future we're talking. Why do I say that I'm doing a 22nd century mission? That's why. Is because it's going to require several technological leaps to get there. Okay, moving along. We need to actually get our total vessel mass less fuel. This is going to be a little bit exciting. So we're going to load up a ship into the simulator, empty it out, and see what we get. Okay, here is our Angel Redskin. This is basically the ship that we'll be flying. We're going to get a preliminary estimate, though. We're not going to get a final estimate for payload, because we need to be able to tweak the amount of fuel that we're loading up. So what we're going to do is we're going to get an initial estimate, then determine how powerful we need to make the engines in terms of ISP, so that we'll have enough room. Then we'll put the cargo in, and then we'll start taking fuel away until we arrive at a final number. So I'm going to go into the scenario editor now, select the ship, and now I want to go to propellant, and I'm going to empty the main fuel tank.
Warning, main fuel depleted.
Master acknowledge.
System reset.
Okay. Now this basically says we're empty on fuel. We still have RCS fuel. We still have scramjet fuel, and we still have APU fuel. As a matter of fact, we should open up the APU ports. Let's see, APU is running right now.
Using external O2. Pitch off. External cooling online.
Okay, we can shut down the APU now, and I want to refuel APU.
Fuel hatch open. Refueling systems online.
Refueling pressure obtained.
APU fuel tanks full.
Oh, and yes, we've been consuming oxygen too.
LOX hatch open. LOX resupply systems online.
Okay.
LOX
pressure.
tanks full.
Got it. Okay, so now we just read off the vessel mass in kilograms. There it is. It wasn't 20, it was actually 40. Whoops. 40,501.6 kilograms. Okay, here we go. Total vessel mass less fuel. Might be a little bit higher than this, but for the time being, 40,501.6 kilograms. And then this is where we start needing to decide what the ISP is going to be for the ship. So, do you remember what the fuel capacity was for the spacecraft? It is 13,396 kilograms. So if the amount of fuel needed exceeds 13,396, we can't fly. Okay, so at this point we're going to determine how MLG the craft needs to be in order to fly. So we need to start getting some ISP values. Fortunately, I have the VIT available so that we don't have to keep going back and forth. We have 8 selections that we can make in ISP, and I have a feeling that we're going to be either 6 or 7. So let's try 4, and we want 4081.633. 4081.633. Enter. Okay, and as you can see, we would need 153,000 kilograms if we had that kind of engine. So that's entirely unacceptable. We can try, actually we need a factor of 10, really. So let's go with ISP value 6. 37,372.55. Now we're in business. I said 32,372.55. Okay. And just for giggles, I'll try 5,400. And you can see we would need 91,000 kilograms. So there we go. That is our loadout ISP. We're going to use the value of 6. So you can see we are still not at the full capability of the XR2 Raven Star. And that was intentional. If you use the full capability, there's almost no end to what you can do with the ship. Okay. Now, another thing that I want to mention too is that I mentioned that the fuel could go up to 13,396 kilograms, but I can install a bay tank to raise that by another 25%. But if we take the bay tank, it means we won't be able to take the probe. So we want to avoid that if possible. Okay, with the main engine ISP done, we're going to take a look at the vessel mass, which is a calculated parameter. And now we have our fuel required. So now, if we look at the chart here, the formulas should read cleanly. So I said we needed everything except columns F through J filled out. So we've got notes, orbits, expected needed delta V, expected needed fuel. Columns F through J are blank. The actual. Okay, something is wrong with the actual burn. Oh, I think it's because I need to create a first mass in order for this to work. So we're going to start with 7,547. Let's pretend after taxi it's 7,540. Okay. I'm going to have to take a look at that. Okay, I knew it went wrong. It was hiding when I opened this up. The mass initial is missing. So we should have 7547.4 initially, and then afterwards let's pretend it's 7,540. There we go. So now we have an actual delta V value. And it's actually pretty realistic. I think that's what I was estimating we would use in the first place. Not counting this. The extra is in case you have like a different runway or whatnot. Or you take too long to taxi, or there's a deer that runs in front of your craft. So we're all set. Okay, so the next thing that we need to do is we need to solve the takeoff time and heading. That should be pretty simple. So we're going to come down here to the flight notes. Okay, we're not flying the Delta Glider 4, and yes. So, we are taking off with as low inclination as we possibly can, which means that the takeoff heading should be 90 degrees. The next thing that we need to do is solve the takeoff time. So for that, we're going to go back into the simulator. Okay, to solve the takeoff time, what we want to do is we want to go into the solar system and we want today. That's going to allow us to work the module as needed. The other thing we need to do is go into modules and make sure that TransX is selected, and it is. So we're good to go. We'll go ahead and load this up. Okay, here's the simulator, and we're going to move a ship. It doesn't need to be our ship, to Wallops Flight Facility. And that's different than Wallops Island. So here is our ship, and it is sitting... Ooh, I don't think... yeah, Wallops Flight Facility isn't installed on this. Well, that's okay. We're going to be using a different simulator, or a different build of the simulator for this. Should be okay though, because I know the area very well, and Wallops Flight Facility is going to be right about there. So get in here, open up the TransX multifunction display, do escape. Now we're going to hit minus twice, actually thrice, to get to Saturn. So we're going to select Saturn, then go back, and we're going to start adding prograde velocity. Okay. Alright, so once I have it to the orbit there, then what we want to do is update the ejection course. Actually, I might need to... no, there is no super. Okay, I'm now starting to get very close, so I can go back to prograde velocity and make that as small as possible. And then we're just going to vary the ejection date. Until we can link up with Saturn. So now I'm going to go to plane change and see if there is any plane change needed here. Okay, we now have something that is sufficient for capture. If we go forward, you can see we'll be coming down past the orbit of Titan. So with that said, we can go back and now take a look at some parameters here. So TransX will have some useful parameters listed on the display. One of those is the takeoff heading. Although we need to advance the date to the current date. So we wanted an ejection date of 59681. So we're going to come up to modified Julian date 59681.47. So we'll say 0.43. Okay, then we're going to do align planes, and we're going to do ELS, and we're going to put in the inclination here, 27.19, and LAN. Longitude of ascending node, 21.29 degrees. And you can see that's about as bad as it's going to get. So we're just going to let time pass and allow that to get a little bit better. Alright, we're just going to see when that bottoms out. Right there. Okay. So you see how that rate just changed to a plus? This is the ideal takeoff time. So we're going to take off at a heading of 101.7 degrees. And let's see. There we go. Our time. April 12th, 2022 at 22:31 UTC. That's it. That's when we take off. So while TransX was being used, we found a better heading than 90 degrees. So we're going to say, should be 101.7, but we can never get fractions of a degree in the atmosphere. So we'll say takeoff heading is 102 degrees. Takeoff time is at, and I'm going to use a special time code format here, 2022, month 04, day 12, and then hour 22:31:00 UTC. That's it. So we have our takeoff time now. That was another solve. That was pretty easy. The next thing that we need to do is fill out this time table. So we're going to get orbits from this column up in here, and then we need repetitions. So I'm going to go ahead and copy all of these orbits into the timetable. Okay, time to imagine the entire trip over again. This time we need to add persistence. All right, so we're on the ground. There's no such thing as an orbit there, 0. Then we ascend. The ascending process is going to take approximately a quarter of an orbit. Then we're going to go up into Leo. What do we plan to do in Leo? We want to do a plane change and then in a transfer injection. That's going to take place in a maximum of 1 orbit, so we're going to do 1 persistence. Then we're going to go on a Saturnian transfer orbit to Saturn. That's going to take us half the orbit, just from the inside to the outside. Okay? And then we're going to be in low Saturnian orbit. So let's see what we want to do in low Saturnian orbit. We want to do an orbit insertion that gets us in there. Then we want to do a synchronization and ring avoidance maneuver. So that gets us, let's see, 1 revolution. That gets us 1 full revolution, and then the second time two and a half revolutions. Okay, then we're in the Enceladus. Oh, wait a minute. Enceladus transfer orbit. Okay, I forgot that was a thing. Alright, 1.5, 1.0. There we go. Okay, and then low Enceladus orbit. Then we want to land. So that's a maximum of 1 orbit. Then we're on the ground. That's 0 orbits again. Then we're going to go back into low Enceladus orbit after takeoff. And there we want to do a plane change and a Titan transfer injection. 1 revolution maximum. Then on our Titan transfer orbit, this will take us exactly half a revolution to Titan. Then in low Titanian orbit, we're going to D orbit, which will take up to 1 orbit. On the ground, that's not orbiting, so 0. Then we go back up to low Titanian orbit, where we do a plane change and then a transfer to Iapetus, maximum of 1 orbit. Then we're on the Iapetus transfer orbit, which is exactly half a revolution. Then we go to low Iapetus orbit, and in low Iapetus orbit, we're going to target a landing, maximum of 1 orbit. Then we land on Iapetus, that's not an orbit, 0. Then we do low Iapetus orbit again. We get into orbit and we escape, maximum of 1 revolution. Then we get into high Saturnian orbit, and we said that we wanted to go when Iapetus was in the opposite direction to the direction Saturn is going, right? So we break off, then we come back around and burn once we've gone 1 Iapetus orbit. That is 1 revolution. Then we go on the Earth transfer orbit. That is half a revolution. And then low Earth orbit. This is actually a lot, because if we arrive at the wrong time of day, it may be up until, I think it's 12 hours before we could get a suitable landing site. Nope, once per day. Okay, so that's going to be, I think a day is 1440, and our revolution is going to be roughly 88 minutes. So that's going to lead to 16 orbits. We'll round up, maximum of 17. So now all I need to do is go up here to the semi-major axis column in column N and copy these values down into the semi-major axis column. Okay, now having all the orbit semi-major axes in place, I have a really nice formula that just converts the semi-major axis to times. So all we got to do is just drag this down, and these ground values we will have to determine separately. So in terms of the amount of time that we plan to stay on Enceladus, these values are in... I forgot to... This formula does not change the major body, so this is incorrect. I'm pretty sure that number is millions of years, so let me fix this. Basically, it's using the Earth's mass for every single calculation. We don't want that. Okay, so in terms of surface stay time, generally what you want to do is wait until there's a synchronous period with another moon. So, for example, we're on Enceladus, and we want to sync up with Titan. So what we need to do is figure out what the synodic period is, and we can do that by figuring out how many days it takes Titan to orbit, which is something like 15.7 days, if I remember correctly. So that's the amount of time that it takes Titan to go around, but then we need to subtract out the time that it takes Enceladus to go around, which is something like 1 day. And in fact, it's not a subtraction, it's an addition. So we want 16.7 days in seconds. 16.7 times 86,400. And what I'm doing is just setting the longest possible time. I don't care what the actual time down there is. It's mainly for oxygen consumption reasons. 1442880. Okay, and then we're going to do the same thing with Titan and Iapetus. Iapetus takes a long time to go around. 79 days. So 79.3 plus the amount of time that it takes Titan to go around, which is something like 15.7. So I want 95 days in seconds. That is 8,208 with 3 zeros. Okay, and that's okay that we're going to be spending 95 days on the surface of Titan, because that's where I said I wanted to set up base. And then lastly, Iapetus, that's just going to simply be its rotational period, because we wanted to leave Iapetus when it is in the going the opposite direction in Saturn's orbit that the sun is going. So that means maximum one orbit. 6886080. And that's it. We should be able to get our entire mission timeline now. This is the entire duration of the mission expressed in different stages. Okay, it is now time to take this table and count it up. So we're going to go up to this area that we've ignored for a while, the phases. So what we're going to do is figure out the amount of hours that it's going to take for each stage. So we want Earth to low Saturnian orbit. We want D87 down to D90. So that selection looks correct as is. Then we're going to do low Sun orbit to Enceladus. Low Saturn orbit to Enceladus. And this is way off. So I want D91 to D93. Okay, now we're going to do the Enceladus to Titan phase. Starting with D94, the stay on Enceladus, and concluding with the end of Titanian orbit, D97. Okay, then we have the Titan to Iapetus phase, beginning with D98, the stay on Titan, ending with D101. I feel like I'm at the DMV. The low Iapetus orbit. Then the Iapetus to Earth phase, starting with D102, the stay on Iapetus, concluding with D106, the Earth deorbit. So now we add all of these together and divide by 24. We have the entire mission duration in days, and we divide by 365.25, and there we go. The mission will last just under 14 years. Now I'm going to go down and just confirm that the numbers are correct and that I'm getting everything. Okay, we're finally getting into the final stages of planning, the last few checks. So at this point, it's time to start finalizing these total vessel mass numbers. I'm going to start opening up the simulator, and I'm going to load it up with exactly the amount of people that I want to take and exactly the amount of cargo and the specific types of cargo that I want to take. And I just want to confirm here that the O2 longevity, we actually don't have a O2 longevity calculated. Well, I'll need to get that information soon too. So I'll complete the loadout table and get O2 longevity. We need to do that before we do the loadout table, because the number of people on board is going to determine the amount of mass and hence the amount of oxygen consumed. But in the meantime, to get you guys excited, look at where we are with this table. So this was blank before, and now you can begin to see what it actually looks like. There's our red line. So that is the amount of burning that will, or fuel burning that will take place. And notice what I said before. We like to get the high velocities taken care of beforehand. There are 47, I think. Yeah, 47 maneuvers to complete. So if we do the halfway point 24, we're already about 2/3 of the way through our fuel consumption. As a matter of fact, the halfway point right here only occurs in the first third of planning. So that's intentional. I like to do less and less and less burns the further we get out. Now, we can't do anything about this jump right here. That's when you come back to Earth. There's nothing really that I can do about that. So I will go ahead and start the finalization. Okay, so I created a new Angel Red XR2 Raven Star. I got it down to the amount of people that was capable, which I did find out. So the largest O2 longevity setting that I can set is 5 years. That's with 14 people though. So if I divide, then we can have up to 4 people, and the O2 will last 15 years. So I loaded 4 people into the craft, and then I loaded my 4 pieces of cargo, the pop-up base, the pop-up control module, the flag kit, and the atmospheric probe into the UCGO adapter, and placed the UCGO adapter into the XR2 Raven Star, loaded every single fuel tank, loaded the APU tank, and loaded the liquid oxygen to capacity. And we finally have an estimate, I shouldn't say an estimate, a should-be exact number. It could change, though, based on circumstances, but we have a total estimated vessel mass less fuel right now of... This is less fuel. I'm not sure how I got such a high number before, but I'm showing 31,369.6 kilograms. I actually forgot something, and that is this number is supposed to include the RCS fuel as well. So that means that this number should be 804 kilograms lower. So that should be 30,565.6 kilograms. And that's correct. However, we do want to keep about 204 kilograms in reserve for the purposes of reaction control. That's actually planned to be consumed. So we're going to increase the amount of fuel here from 65 to 69 and then add 200. So we're going to get 30,769.6 kilograms, requiring this much fuel, and this is going to be split 600 kilograms load into RCS tank, and then we'll just note that 204 kilograms already in the tank is for RCS, and the remaining, so that's going to be 5,134.4 kilograms into main tank. Okay, I just realized these numbers, the launch vessel mass is going to change yet again. The reason being is because there's a couple deployments that we're doing. We're going to be releasing the atmospheric probe, and that's not coming back. So we need to subtract out the weight of the probe, and we also have to subtract out the weight of the scramjets as after they deplete. Okay, well that took a long time and a lot of thinking, and unfortunately I had to break some of my formulas, but I managed to do it. The nice thing about this actually gets us 600 kilograms less fuel required, which in real life would translate to a decrease in the price tag. So that's pretty nice. So our new vessel mass less fuel is 27,063 kilograms, which subtracts out both the scramjet mass that we're going to burn on the ascent as well as the atmospheric probe mass. So this changes all the numbers, and I've updated those. Yes, I've also updated the launch vessel mass, so that should now be correct. And then I came up here, and this is where we start to see the formulas changing. So just to describe what I did with these formulas, I highlighted this column different so that I would know about that. So everything uses the mass less fuel and the probe and the scramjet up until this point. Before this point, we have the atmospheric probe. So what I had to do is I had to say, okay, I want you to tack on the atmospheric probe to the minimum fuel, which or the minimum weight, which appears in 2 locations in the formula. And then I had to subtract out all of the cumulative delta V that would add based on all of these numbers, assuming the new values. So I subtracted those out and basically had to do it a second time with the scram fuel. And this made a much bigger difference because the scram fuel is so much heavier. So I added on to that sum the weight of the scramjet fuel in both cases, and here's the 600 cumulative out. So all of this delta V here, all of this mass that was going to be used for delta V's is no longer necessary. So our new total is now 5,122 kilograms. Finally, moving along now, we're going to fill out the loadout table. So we should just confirm that everything adds up here. Let's see, enter estimated maneuver delta V here. 5,122 kilograms, 5,122 kilograms, 5,122 kilograms. Good, so we're triple checked. The other thing that I needed to check was the engine power. I'm not exactly sure what that is set to right now. The engine power can be changed in the config file to do 2 different versions. I think there's what's considered default and easy, and usually I think I have mine set to default. So I just want to confirm that that value that we're seeing is the default value. Here we go. Maximum main engine thrust per engine. Main engine thrust equals 1 for realistic, 192 kilonewtons. Oh, okay, so this is not correct. The reason why this is saying 260 is because we were actually set up for the Delta Glider 4. So good thing I did that. This is 192 kilonewtons times 2 because we have 2 engines on board. Time of flight, enter amount from B23. That's going to be that one right there. B23. That's because I extended this. Time of flight, 14 years. Alright, I'm going to just add in the notes here. Amount shown is one engine. Because I'm going to come across this, and some days I might be like, oh, okay, 192 kilonewtons times 2 will give me the total engine power. And other days I'll come and see this, and I'll be like, okay, the times 2 engine power is 192 kilonewtons. That's both engines. And then I'd be very angry to find that that's wrong. Okay, so we can clear this note here. O2 years on board. Okay, so we need to figure out O2. Okay, O2 years in the cargo bay is going to be 0. I'm not carrying any extra oxygen. I guess we could if we really wanted to, although I don't know how close we are to the maximum payload bay mass. Anyway, O2 years in the tank. This I'm actually going to need to take a look at what the what actually shows up, because it'll tell you a certain amount of years, and it turns out to be slightly different than that. So let me get this. Okay, O2 years in the tank. I'm reading 6,406 days plus 14 over 24 hours plus 53 over 1440 minutes plus 20 over 86,400 seconds. And we've got 6,406.62 days. So we can round down to 6,406. Means we have 17.53 years in the tank. So we have 3 extra years for contingency just in case. It's always a good idea to fill to the top with oxygen, because it is always possible to find a fuel shortcut. You're not going to find an oxygen shortcut. So I'm a lot closer about that. Okay, then we're going to see the vessel table for convert. Oh yeah, we can... I'll change this to as read from vessel. And this is... see vessel info for conversions. There's nothing in there, so that's gonna blank out. Okay, payload. Okay, luckily I already put this information together. We just need to recall it from my list. Okay, so the very first thing we're going to be taking is a UCGO Universal Cargo mod XR2 adapter. This is 1,253 kilograms. We're also taking a base control module. This is going to take 3,217 kilograms. Then we're taking a flag kit, which is 54 kilograms. And we're taking the atmospheric probe, which is 356 kilograms. And lastly, we're taking the base module, which is 2,874 kilograms. For a grand total of Thought I had it listed somewhere. Oh, there it is. 7753. And also a note that atmospheric probe will be jettisoned. And that's just a note for me that it's leaving and it's not coming back. We're going to, believe it or not, we're going to bring everything else back. We're going to bring the pop-up base back. We're going to bring the flag back. We're going to bring the XR2 adapter. We're going to bring the base adapter. Number of passengers, we're going to have 4, is what I said we were going to have. And the last thing was the RCS fuel in kilograms. Let me just make sure that this doesn't mess with any of my numbers here. So the total vessel mass, 35,891.54. $35,891. .54. Okay. 5122. Okay, we're good. And in fact, because I am counting 204 kilograms, or I'm counting 600 kilograms in here as fuel, we're going to say that we're actually only carrying 204. So even though the RCS tank is big, what we're going to do is we're going to move fuel over to the RCS, or from the RCS to the main tank as it's consumed. So let's see, that's the engine power. I guess this should be listed over here. 192 kilonewtons times 2. Much better. Okay, filled out completely. All right. So there's the 10th step. The loadout table is complete. The 11th state is to validate the action items. Okay, this is it. 11, 12, and 13 should roll right out. Actionable items. Circularization burn deserves its own line. Let's confirm. Yes, we have Leo circularization. It has its own line. This is dismissed. To know when to burn for Trans-X inclination adjusts, align plane, ELS, inc, and LAN values from Trans-X. Let's see. Align plane, ELS, enter inclination, and LAN values from Trans-X. Okay. This has been incorporated, dismissed. To perform the arrival inclination adjustment burn, open align planes, ref target, base, or moon, R inc. Burn until ascending nodes and descending nodes are equidistant. Let me make sure that that is here. That is this instruction. This one is dismissed. Landing fuel economy instruction should be at the first landing, and it is, so this one is dismissed. Only had an 18-degree plane change thanks to the help of ejection orientation on Trans-X. Let's see if that, we would want that at the first plane change. We could also, actually this affected on the way back. So let's do plane change aligned to Earth. We'll set that in there. Paste values, perfect. And get rid of the information related to this particular flight. So we said try ejection orientation on Trans-X to save fuel. Okay, you are dismissed. There is a constant perturbation present returning from Uranus. It ultimately caused 10 MCCs totaling 812 meters per second. We have MCC bank here with 812 meters per second. You are dismissed. Okay, if there's one burn to plan right, it's Earth arrival from the outer solar system. So let's go ahead and confirm that actually that's not in place. So we're going to copy this and we want it right here. Okay, this item is dismissed. A final plane change should exist to precisely align the re-entry path. Here is my added atmospheric entry planar alignment burn. This is taken care of, dismissed. A perfect ejection burn will have 0 relative inclination, 0 delta V, and 0 semi-major axis at burnout. That's very useful for the trans Saturn injection, so we can stick that in right here. Okay, you are dismissed. To record the data log, you need to press start and then log. This is relevant when we go deep into the Saturn atmosphere. So we're going to Saturn orbit insertion right there. Okay, dismiss. Whoops, I had the wrong location highlighted. Okay, read the previous flight's MIT for notes, so you'll need to know when you need 812 meters per second in MCCs. Let me do that real quick. Okay, the only thing that I picked up from reading was to add this ejection orientation course for the first orbit injection. So, we have read the previous flight, SMIT, that's done. So this has become the actionable items from this flight. Step 12, prepare the scratch zone. That's just right here. We're just making sure that everything here is clean. Use for real-time notes and math. We'll get rid of that. Move these up. Then I have the information related to where to release the Saturn probe, and then the low pass target altitude for us when we arrive, which is right there. The rest of this is clean. I have no concerns, and that was it. Step 13, prepare the flight notes. So we have the takeoff information, the cargo loadouts, estimated masses, and this is the official. We can't fill this in until we're actually on site. Okay, so the good news is the flight notes are prepared. The really, really, really bad news is, unlike the Delta Glider 4, the XR2 Ravenstar consumes oxygen mass and doesn't replace it with carbon dioxide. This means that the mass of the ship is actually changing at a constant rate, which deals with time, not position, which means yet again I have another changing mass parameter which I have to update here, because the mass won't be constant. This will be constantly changing, and it's huge. We're loading as much oxygen as we are fuel. So, maybe I can cross-correlate them. Oh my gosh, I feel like I'm watching the end of a Terminator movie. You know, I do the math, and then I think it's over, and then all of a sudden, it starts up again. So, I think I solved the issue. What I did was I had to add a new column, which is occupied in M right now, with the O2 burn. what I realized was only about 160 days, or less than 1/30th of the mission, actually takes place at Saturn. So what I could do is hold the O2 remaining relatively constant at Earth in both cases, and then apply a simple subtraction across the time that will be at Saturn. And then on the way to and back, the MCCs, those were the tricky ones, but it's just 6 values. So I basically said, okay, probably the first one's going to occur 6 months in, the next one 2 years in, the next one 4 years in. That's typically how they run. Okay, so I got this O2 remain column. And then all I needed to do was say, okay, well, add whatever fuel is present onto the mass that's already present. And I had to adjust all 3 of these equations, but the logic is there for all 3 equations now. So, interestingly enough, we have the same value, the same amount of fuel as before. Okay, I think I have it now. Hopefully. Alright, anyway. So, what I did wrong was I said, okay, use the value from here on out, but because this says expected fuel to complete this and all future burns, what I need to do is take the average of the ones between this burn and the end. So the average remaining oxygen is sort of a rolling number. In this case, it's 2761 or somewhere thereabouts. So this brings me down about 400 kilograms, and this makes sense because the thing that was alarming me was the fact that the value of needed fuel was exactly the same as what it was the first time, and that should not be the case, right? I should expect to save some fuel. So now you can see there's a little bit more of a reverse falling parabolic curve from the get-go, and that makes sense because as time goes on, we are consuming less or we have on board less and less oxygen. So I believe we're okay there now. In fact, I can drag this down and you can see what this looks like without this done. So there's the 4887 number. So this is what it looks like without accounting for the oxygen. This is what it looks like when you do account for the oxygen. So we save about 450 kilograms, and based on my previous flight experience, that sounds like it's a correct number. Hopefully it is the case. Or else we're going to have a really short flight. So we still have the same fuel budget in here, same safety margin rather. Delta V doesn't change. Delta V is Delta V. That's a natural law. I also had to add this LOX line here, and we get the final launch vehicle mass, which, let me just confirm that it is correct. Yes, it's using the one up there. However, we have a fuel disparity. This equals D86. This is D86. Now, there's got to be more to it. Oh, it's that one. 4615, that's incorrect. 4615 found by taking a launch vessel mass minus scramjet minus atmospheric probe minus the vessel mass without the fuel, and then minus the liquid oxygen mass. Which means there's got to be an issue with how this is being calculated. Oh, wait a minute. Oh my gosh, I'm an idiot. 4615, not 4404. I thought this was saying 4415. Thank goodness I shouldn't say thank goodness. I really hope I'm done now because my brain is starting to turn to jam. So, we have 4615 fuel required. That looks like the right number. And now our final launch mass is 35,385. And the last thing I did was again split the fuel up with 4615. 600 goes into the RCS tank, and there's remaining 4,015.771 kilograms that goes in the main tank. So I believe we are now finished the flight notes. The last thing for me to do is the final inspection. I can't do that now. The final inspection is intended to take place during a time that my mind is not melted. So we're done for the day. I'm going to go ahead and end the video here. When we come back, we'll pick up with any changes that have occurred due to that final inspection. We'll review those changes, and then we'll begin final preparations before the launch, assembling checklists, building the scenario itself, figuring out how things are going to get loaded, who our passengers are, that sort of thing. Alright, I will see you guys next time for all of that. Thank you all for joining me, and I have a tremendous amount of respect for you if you stayed watching through all that time. Thank you, and bye-bye.